Hello, sir. சுகந்திருப்பா ஸ்டாப் மை வீடியோ இதுவா
Sir, good morning, sir. Sir, கேக்குதா?
ಕೇತೆ ನೋಡಬಾ ಇಲ್ಲಿ ಇಲ್ಲಿ ಬಿತ್ತದಬ್ಬ ಡಾಂಗ್ಲೆಲ್ಲ
Daniel, sir, good morning, sir. Can you able to hear me? Daniel, sir, good morning, sir.
Good morning, Mati. Are you okay?
Daniel, sir.
சொல்லுங்க ஹரி.
Sir, okay, sir. Is it fine, sir?
Fine, fine. Thank you, Hari. Thanks for your support.
Okay, sir. Okay, sir.
Thank you.
சார் நீங்க மூர்த்தி பி மூர்த்தின்னு வந்திருக்கீங்க தானே சார்? அது உங்களை ஹாஸ்ட் பண்ணிடுவா சார் நான். ஆக்சுவலா இப்போ வந்து ஐ மேட் யூ ஹாஸ்டிங் சார். அப்படிங்களா? இல்ல ஆக்சுவலா நான் உங்களுக்கு பண்ணிட்டேன். இனிமே நீங்க தான் சேஞ்ச் பண்ண முடியும். நீங்க அவரை ஹாஸ்ட் பண்ணீங்கன்னா சார் ஒரே ஒரு ஆப்ஷன் மட்டும் பண்ணணும். உங்களுக்கு மேல பார்ட்டிசிபென்ட்னு ஒண்ணு இருக்குல்ல சார், மொபைல்ல இருந்து பண்ணிருக்கீங்களா? ஓகே, அப்போ ஒண்ணும் இல்லைங்க சார். ஜஸ்ட் பார்ட்டிசிபென்ட்ஸ் இருக்கு பாருங்க சார். அந்த இதுல அந்த பட்டன் கிளிக் பண்ணீங்கன்னா ஃபுல்லா லிஸ்ட் ஆகும் சார். அதுல வந்து டேனியல் சாரை செலக்ட் பண்ணிட்டு, இல்லைன்னா நானே பண்றேன் சார். ஹலோ சார். இப்போ நான் டேனியல் சார் ஹாஸ்ட் பண்ணிட்டேன் சார். இடையில மட்டும் சார், இப்போ நீங்க அவர்கிட்ட இருப்பீங்களா சார்? அவர்கிட்ட தானே சார் இருப்பீங்க?
unmuted. Good morning, dear participants. Good morning, dear participants. I hope you can able to hear our audio.
Yes, sir. We can hear you.
Thank you. The participants are joining. We will start the session soon. Kindly mute yourself when you are entering the portal. Thank you.
Sir, good morning. But there is no video is visible.
Dear participants, very good morning to all. On behalf of Sri Ramakrishna Engineering College, we welcome you all for this one-day webinar on diverse application of nanomaterials. The session will start soon. The first speaker is preparing to log in. Once he logged in, we will start the formal welcome address and opening remarks session. Kindly wait. Thank you very much for registering in this one-day webinar.
Good morning, participants. I hope everyone is safe and healthy. So the first speaker will log in 1 minute. Please wait. Thank you.
Good morning, Daniel.
Good morning, Professor Dr. BSM.
Yes.
I respected distinguished speakers, Dr. Professor B.S. Murthy, Director, IIT Hyderabad, Professor S. Balakumar, University of Madras, Dr. Tiju Thomas, IIT Madras, my dear faculty friends, participants, students around the globe. A very good morning to everyone. Thank you for joining with us today for this one-day national webinar on diverse applications of nanomaterials. On behalf of Sri Ramakrishna Engineering College and Department of Nanotechnology, and on my own, it is my true pleasure to welcome you all for this national event. Nanotechnology is an emerging interdisciplinary research area, and it is developing exponentially throughout the world. To understand the momentum, in 2007, Government of India, under the Ministry of Science and Technology, had launched an umbrella program, namely Nano Mission, to encourage the researchers from various disciplines and related research activities by providing research funds. Applications of nanotechnology ranges from diagnosis and treatment of disease like cancer, efficient energy production and management systems, strengthening of materials, structural components, miniaturization of electronic devices to quantum computers. Probably in future, numerous nano-based products will flood the market, and the students who studied the nanotechnology will have the best possible scope in R&D sectors of almost all the premier industries and national research establishments like DST, DRDO, ISRO, and CSIR, etc. To keep up with the current trend, SNR Science Charitable Trust had established Department of Nanotechnology in 2012 with the seed grant of 3 crore rupees. The department, equipped with state-of-art research laboratories and expert faculty members having a specialization in various disciplines and involved in active research. Of course, the department is a recognized research center by Anna University of Chennai, and have a full-time research scholars funded by various research schemes from the government agencies like DST, CSIR, SRF, as well as SREC Institutional Fellowship. So far, 2 full-time PhD scholars have completed their PhD program. One is working in city-based college, and another one working as a postdoctoral fellow in University of Madras. I'm happy to announce that the department has 4 centrally funded projects to the tune of 1.13 crores from DST Inspire, CSIR MR, EMR, DST FIST and DST Women Scientist Scheme A. Of course, the department also has the research project funded by the industries like Cameroon's Converger, Roots, Erythral Rhythm, etc. The department houses advanced synthesis, characterization, and fabrication facilities, and also it extends its facilities to the aspiring researchers from other institutions with limited facilities at their parent institution at a nominal fee. We are organizing this one-day national webinar today, inviting eminent personalities from premier academic institutions. Professor Dr. B.S. Murthy, Dr. S. Balakumar, Dr. Tiju Thomas will be the distinguished keynote speakers of the national event. The primary objective of this national webinar are to upgrade our knowledge in the field of nanotechnology and nanomaterials research through exclusive and relevant keynote lectures. You can share the recent research progress to the fellow scientists and the participants through interactions to extend our discussion and potential scientific collaborations with eminent professors, scientists, and experts. We think the various interdisciplinary keynote lectures can initiate the intellect in the field of nanoscience and technology among the participants. The event, I'm sure, I hope the event will be a good opportunity for them to keep update with the eminent personalities. With these few words, a very warm welcome to all of you once again. I hope this national webinar provides you with a forum to exchange scientific ideas, inspire new research, and new contacts for closer cooperation so that we can envisage the future of promising development, nanoscience, and technology. I wish you success in your present endeavor and a very fruitful and pleasant lecture session. Stay safe, stay healthy. Thank you very much. Yeah, before handing over the session to Professor Dr. B.S. Murthy, I would like to say a few words about him. It is not easy to say about him because he's a very good, wonderful.
Daniel,
well
I think it is not necessary, if you don't mind. Okay.
Throughout the globe.
So shall I start my session, if you don't mind?
You can go ahead, please.
Sure.
Thank you very much.
Thank you. Friends, I'm sorry, I usually don't like introductions. So that is the reason why I stopped him. Forgive me for that. I'm B.S. Murthy. I've been with IIT Kharagpur for about 12 years and then IIT Madras for about 15 years. In last 9 months, I am here at IIT Hyderabad. So we have been working in the area of nanomaterials for quite some time. I would say about 25 years now. Various metal-related nanomaterials. Okay, I can say, and got quite a bit of excitement in that particular field. But more importantly, what I want to share with you today is not just our research on the nanomaterials area, but more on how to peep into these materials and to see interesting features of materials at a very, very small scale. So basically, I'm going to talk more about microscopy as such, and a special microscope, which we call it as an atom probe, is what I thought I will share with. Okay, so in that context, this is a very, very special technique which in India at the moment, there are only 2 such units in the whole country, and one at IIT Madras and one at IISc Bangalore. And this is what I'm going to share with you. Just to tell you that, the interest to look at things which are small, I think is a curiosity that is always there in people. Long back also, people tried their best to peep into materials which are very small, and also to see if there is anything else that I am not able to see from the outside, and be able to see what is there inside a material. Okay, so what is called microscopy has started almost like about 1600 or so, and there are images which I showed you here, which is done by Robert Hooke in 1665. And people are now talking about not just a microscopy as such. People have gone to the extent to talk about what is called 4D microscopy. It is not even 3D microscopy that people talk about. So what is happening as a function of time? Okay, how does something evolve at a very small scale as a function of time? This is another area large number of people are interested. And this went on to the extent that particularly I am a metallurgist. To see metals at a very small scale, people use what is called optical microscope. Everywhere in most of the institutions you will find it. So that was the first time with an optical microscope people were able to see inside a steel. What you see, the microstructure on the right side is a steel, where there is something called cementite and ferrite. Lamellae is something that people were able to see only with such an optical microscope. But the problem with these microscopes are there is a limitation on the resolution that you can achieve. For example, a typical optical microscope can give you a resolution of about 200 nanometers. But the whole world of nanomaterials has evolved, where people usually define a material as a nanomaterial when the size is less than about 100 nanometers typically. So how do I see smaller things than that? So this kind of an interest was evolving in materials, and it also has certain practical significance. For example, what you see on this particular slide is the evolution of an aircraft. Long back, there is a guy by name Wilm who wanted to see, can I make a light and strong material? And he knew that in steels, if I heat a steel to high temperature and quench it into a water, suddenly the steel becomes strong. So he thought, let me do this with aluminum. And he kept on doing it. And he, at some point of time, he realized that just by quenching aluminum alloys do not become strong, but by doing what is called aging, that they will become stronger. And a material called duraluminum came into picture. And now, most of the aircrafts are made of those. But what is the reason for this particular aluminum alloy to become strong? What is happening during this aging process? Nobody knew at that particular time in 1903 when this was discovered. And people had to wait almost for about 30 years for the evolution of a new microscope called transmission electron microscope. And what you see, a microstructure on this particular slide, is taken from one such aluminum alloy, where the microstructure shows extremely fine precipitates, which are of the order of few nanometers in thickness. And this was possible when somebody discovered by name Ernst Ruska, has come up with a TEM in 1932. And incidentally, he had to wait almost for about 50 years to get his Nobel Prize. In 1986, when people were giving Nobel Prize for STM, scanning tunneling microscope, along with them, Ruska also received his Nobel Prize. And that was the beginning of peeping into materials at a very, very small scale. If we don't have a TEM, we would not have been able to see things at that scale of nanomaterials. Why nanomaterials? Now you can even see atoms. Okay, for example, this microscope that you see at IIT Madras, it's called Titan, costed us about 17 crores. And you can actually see atom by atom in a 2-dimension. What you see on the right side bottom is a silicon, the interesting dumbbell structure of silicon atoms, where each white dot that you see is an atom. Okay, and we can get a resolution with this particular microscope of the order of around 0.6 to 0.7 angstroms. So less than an angstrom resolution is possible with this kind of high-end microscope. But the only difference is this microscope gives you a 2D image of a material, which is basically a projected image, because if you know about TEM a little bit, an electron beam goes through a sample and then comes out of a sample, and what you see is a three-dimensional information of a sample projected onto a two-dimension, and you see a 2D image. But people were interested to know, can I see atoms in 3D? How does a material look in 3D at the atomic scale? So there has been further, deep inquiry into materials, and that's how many things have started later. In addition, TEM also was helpful in discovering a new type of material called quasicrystal. In fact, if those days TEM was not there, the so-called tenfold would not have been possible, because X-ray diffraction typically does not show you that. And if you take an XRD, and put a quasicrystal through an XRD, a typical powder XRD, you will never be able to differentiate between a crystalline material and a quasicrystalline material. So in 1982, for the first time, Dan Shetman put an aluminum manganese alloy, rapidly solidify alloy, into a TEM and was able to see a tenfold diffraction pattern that you see in front of you here. And he was amazed, because till then nobody has seen such a tenfold, and people called such kind of symmetry as something forbidden symmetry. Okay, so that was the first time, and there was a lot of opposition to him. He kept on pursuing that, and in 2011 he gets a Nobel Prize for what he has done. And all this was possible again by such microscope called TEM. And you can see here, this is an image taken from one such quasicrystal, where each white dot that you see is an atom. And if you carefully look at it, you will see a pentagonal symmetry and the tenfold symmetry that I am talking about inside the material. And then in 1955, there has been another parallel group, Professor Muller and his collaborator, a postdoc with him by named Kanwar Bahadur, incidentally an Indian from NPL, National Physical Laboratory, went there, and they were interested to look at how atoms are on the surface of a material, particularly for catalysis kind of applications. Surface matters a lot, and how atoms are arranged on the surface can play a significant role on how a particular surface behaves. So they were trying to look at this, and in 1955, for the first time, they were able to see an image like this. Okay. Of course, this is not an image from 55, but much later, Professor Ranganathan, my PhD supervisor, did a lot of work on this, and this is one such image where each dot that you see is an atom again. So this is taken from the surface, what is called field line microscopy, and where you can clearly see the symmetry in which the atoms are. For example, this clearly shows the fourfold symmetry, which is unique of this particular platinum, which is an FCC material. So people were able to see the crystallographic symmetries of materials. People were also able to locate where the atoms are. People also were able to locate where there are defects in atomic structures. For example, certain vacancies people are able to see, even certain dislocations people were able to see. All this they were able to see. But in the whole process, what is missing information here is I do not know what atom I'm looking at. I just see that these are basically images of atoms is what I know. But if I have a material which is not a pure metal, it is an alloy, let us say, or a compound, let us say, and I want to know where which element inside that compound or an alloy is sitting, is something the field ion microscopy does not show. And that's where people had to wait for some more time. Okay, and this is the young gentleman whom you see, a very lean man. On the right side, he is Professor Ranganathan at his young age. He is more than 75 now. Okay, and this is what has come out later. People wanted to do what is called tomography. We all are aware of tomography, for example, CT scan, that people talk about it if somebody has some health problem. And this is basically a similar CT scan, but done at a much smaller, length scales and with a very high resolution. So this is where it shows the field of view and the resolution, and the smaller the resolution that you want, you need to go to techniques such as atom probe tomography. We have X-ray tomography also. A number of other tomographies are available, and this atom probe tomography is the one which gives you the smallest resolution possible. And this is how the whole field evolved, starting from the field and microscopy in around 1930s or so to atom probe tomography, which has evolved as a 3D AP in 1986 to what is called local electrode atom probe, which came in 2002. And that is what everybody uses it now. What is called LEAP, everybody calls it as. This is how a LEAP looks like, which we have it. This is the first LEAP that has come to India at IIT Madras. We have set up. What you see on the background of this particular thing is how the sample is handled, and the sample is kept inside the chamber, the white colored box that you see, and then the image that you obtain from that is what is seen on the screens there. And you see images like this, which is there on the right side, which is a rotating image, which is nothing but a metallic tip, for example, a sample where each dot that you see is an atom. Okay, and the colors that you see are indicative of different type of atoms. Okay, so we can give fictitious colors to various, atoms inside materials do not have any colors for that matter, but we can give fictitious colors to different type of atoms. And how do we do this? The whole principle is like this. You have a sample which is like a sharp needle, and you put a local electrode in front of that. As you can see, I am showing with my cursor, and you use either a laser or a pulsed beam, pulse the voltage. With that, you knock off an atom from this, and this local electrode, it goes through it, and then there is a reflector where it gets reflected and comes onto a screen. The moment it comes and hits a screen, okay, the screen will come to know that an atom has hit it, and the XY location of that can be retained. In addition, the time it has taken from the time it has been knocked from the surface to the time that it takes to reach the detector is also noted. And this time is a function of the mass. It's basically a mass spectroscopy in one way. Time of flight measurements, we call it as. So from the time I can know the mass, from the position where it comes and hits, I know where it was in the sample. So the XY location of that can be retained here. And once one layer is knocked off, you go to the second layer and third layer. And with that, you will also be able to know the Z position, how deep the atom is. And if you reconstruct each of these layers, what you get is an image that is there on the right side. So basically, you are reconstructing the whole sample, okay, in a layer by layer mode, like a CT scan. Typically, CT scan also you take layers and all the layers are stitched inside a computer. Exactly, you do that, and with that you will be able to see this kind of information. But how do you prepare that kind of a needle is a very important thing. The needle should be as sharp as the diameter at the tip should be approximately around 50 nanometers or so. If you don't have, you will not have a field enough generated to pull an atom from the tip, because it's basically a field that you generate. If the field is large enough than the interatomic forces, an atom will be pulled out. So for that, you need a very sharp tip. Long back, when I started my life with atom probe tomography, this was around 1999 to 2001. For 2 years, I worked on atom probe, and that was the time we used to use a technique called electropolishing technique, where you take a sample in the form of a needle or a ribbon, and using an electrolyte, you sharpen the needle, and then you will put it into a TEM to ensure that the needle is very sharp before you put it into atom probe and use it. And whereas now we have techniques such as focused ion beam that has come into picture. FIB, people call it as. FIB is basically an SEM. Okay, the only thing is we call such an SEM as a dual beam microscope, where you have one beam which is an electron beam to see the sample, another beam which is an ion beam to cut the sample. It's basically a kind of a milling machine or a drilling machine, that if you can call so. So you can take a sample and cut the sample using a focused ion in such a way that from a flat plate-like sample, you can cut from both sides so that you have a small portion here which is of interest, and cut that portion. And then what you do is take a needle or a sample holder, which we weld it to this. Everything is being done inside the SEM. Please understand this. This welding is done by depositing plasma at the junction between the two, and then you cut the second side so that you are basically lifting a sample like this. Once you lift the sample, bring it and put it onto a micro pillar, and then again join these ends with again a platinum. So that means you have one more micro welding that is happening, and after that, using again ion beam, you sharpen the sample. You can see that all this is happening inside the SEM, and you can see how they happen. And this tip is now having a diameter of approximately about 50 nanometers or so. And with that kind of a sample, you can put it inside the atom probe and do. When I started this long back, we didn't have FIB those days, and we used to do electro polishing. And the reason why I went into atom probe those days was we wanted to study how oxygen influences metallic glasses. There were those days people making metallic glasses in different groups, and what is interesting is in some special type of a metallic glass, which is zirconium based metallic glass, depending on the group that is working on that, one group reports that when I take this glass, crystallize it, I get a crystal. Another group says when I crystallize it, I get a quasi crystal. The composition of the alloy is exactly the same. So people had always confusion, what is happening inside? Then I had a hunch that possibly oxygen is playing some role. So what we did was we produced 3 different types of glasses exactly with the same composition overall, excepting that the oxygen content we varied in the alloy. There are ways to do that. I will not go into the details of that. What is interesting is when you increase the oxygen content to a higher level, you start getting 2 DSC peaks, differential scanning kilometer, if you put the sample. Whereas if you have very low oxygen content, you get only 1 DSC peak. And if you take this material and do some kind of a heat treatment inside the DSC or in a furnace and measure the XRD pattern, you will see that the alloy which has very low oxygen content, when you heat it from an amorphous state, it becomes a crystalline state. All these blue dots that you see, the peaks, are all basically Zr2CuAl. Whereas if you take a higher oxygen containing alloy, initially it becomes a quasi-crystal. These 2 peaks that you are seeing belong to a quasi-crystal, and finally this quasi-crystal vanishes and gives you a crystal. And we wanted to know, does it mean that oxygen is stabilizing a quasi-crystal? That was a hunch I had, okay? But unfortunately this XRD will not tell me that. And we went to the TEM, went into what is called GIF image those days. Those days still Titan has not come, and with that, you know, oxygen is a lower atomic number element. So looking at oxygen and seeing that this oxygen is getting concentrated in a quasi-crystal is very difficult to obtain. But what is more interesting is, for example, every one of these circular particles are all quasi-crystalline particles. How do I know? I put my electron beam on each of the particle, get a diffraction pattern, you see the 5-4 symmetry very clearly. Okay, and we wanted to see whether oxygen is getting concentrated into these particles, and these what is called chemical spectroscopic technique on the TEM was not able to give. Something like a EDS cannot give you. So then when we went to atom probe, we were able to see that there are small particles inside the sample. Here, each box that you see is containing one particular type of atoms. The top one is zirconium, copper, aluminum, and oxygen. And this particular small particle, which is about 2 nanometer kind of a particle, has a lot of oxygen into it. Of course, those days, the atom probe itself that was available was not a very efficient atom probe. With a lot of struggle, when you wait for 24 hours of collecting atoms from the sample, you are able to collect about 400,000 atoms or 500,000 atoms. Now with the new atom probe, in about 15 minutes, you can get 5 million atoms. That is what is the difference between a LEAP and an older type of atom probes. And with that, we were able to get satisfied and were able to prove something which a lot of people appreciated. And now people are trying to look at these things with a new atom probe in a much, deeper insights. And one such example I wanted to give is, again, being a metallurgist, we work a lot on steels, and some of the special steels that people are making now are called ODS steels, oxide dispersion strengthened steel. That means I take a steel and put some oxide particles into it, yttria nanoparticles. When I put nanoparticles into steel, the steel gets a very high, what is called creep resistance. That means high temperature resistance. These are being used for fast breeder reactors. We have been able to collaborate with IGCAR Kalpakam, NFC, and DMRL. We're able to produce a 4-meter long tube of a steel with these nanoparticles embedded into them. And such a tube, if you look at the mechanical properties, it has a much higher yield strength than the traditional materials, even at 600, 700 degrees centigrade. And if you want to know what is happening, why, and you can carefully see there are extremely small particles inside. You can go to a TEM and see these small particles. But what is the nature of this particle is very difficult to find out using a TEM. Whereas if you go to an atom probe, you will see a small particle, 2 nanometer particle, which is that yttria nanoparticle. You wanted to know whether it is really pure yttria or something else is happening after I have embedded into the steel. Now, if you carefully look at it, you can see yttrium atoms, oxygen atoms. There is also chromium in it. There is also titanium in it. And obviously oxygen in it. So we can find out how these are. And with that, this was done in Iowa State University. Those days we didn't have an atom probe at that, but now we have our own atom probe. With that, if you look at in our atom probe, you can see this particular pink sample that is there in the middle. Every dot is pink dot is an iron atom, and inside you are able to see some green color patches. These are all extremely small particles. The size of each particle is about 2 nanometers or so. And inside that you have yttrium, titanium, and oxygen. Okay, and this is something which we call it as a national facility for atom probe tomography, which has been established with about 40 crores, and where all the institutions that I have put here, about 7 IITs, 6 IITs have given about 2 crores each. ARCI has given 2 crores, and DST Nano Mission has given about 25 crores. And with that, we have been able to set up. What is unique about this is a remotely operable atom probe, where anybody can send us a sample. We polish the sample in a fib. Let us say fib is seen here, okay, and put it into the atom probe, which is seen on the right and left top. Once you put it, we get connected to any of these users who are sitting in various IITs, and they will have a small workstation where there is a connection provided for this, and they can operate the machine sitting at IIT Bombay, IIT Delhi, and so on and so forth. That is the beauty of this. This is the first of its kind, and it runs in 3 shifts. We have 3 operators running in 3 shifts on a 24/7. I don't think there is any microscope anywhere which runs like this. That's the beauty of this, and we have about 8 partner institutions in this. This is a wonderful unit which has been working for the last 2 years. I'm extremely happy. A lot of good research is coming out of this. And this is one such sample. You can see that iron, tungsten, chromium, all these elements are all uniformly distributed inside the sample. But you see yttrium, titanium, and oxygen are there inside the sample in those small particles that I am talking about. Okay, so each dot is an atom. So you are able to see atomic resolution of these. And one can also see various materials. This is one so-called what is called a high entropy alloy, which we have been working on in recent times. It has 5 elements. I want to know whether all these 5 elements are uniformly distributed or not. And if I carefully look at it, yes, they are all very, very uniformly distributed. I can see oxygen, I can see nitrogen, I can see carbon. In fact, there are people who also are reporting that they are able to see hydrogen. Okay, there are some reports in recent years that hydrogen has an atomic number of 1. That's the smallest atom, and most of the other techniques that we have, such as EDS or WDS, you will never be able to see small atomic number elements. So this is one technique which can even show you hydrogen. And at the same time, such alloys, multi-component alloy, depending on the technique by which you prepare them, it is possible that you can have a heterogeneities inside the sample. So here you have more or less like a 2-phase microstructure. One phase is rich in one particular type of element, another phase is rich in another type of element, and this kind of things can also be found out very easily using atom probe. We also wanted to see whether there is any segregation of certain elements at the grain boundary in these high entropy alloys. So we made what we can do using a fib is that you can cut the sample in such a way that the grain boundary is along the axis of this tip of the sample. We can prepare an atom probe sample using a fib such that the grain boundary goes from top to bottom here in a along the axis. And once you put it into an atom probe, you can now see whether any particular element is getting segregated at the grain boundary. Interestingly, in this particular alloy, we don't see any such segregation, saying that the elements are uniformly distributed within the grain and at the grain boundary without any special affinity to get segregated at the grain boundary. People are also interested in looking at steels, for example. Variety of materials people are looking at. For example, they wanted to see whether carbon gets distributed in a particular phase. In steels, we know carbon gets enriched into one phase called austenite and gets depleted in another phase called bainite. I mean, what is called ferrite, and people are interested to do that. So you can actually see a very small atom as carbon also, whether it is. Rest of the elements are all uniformly distributed, excepting carbon, which is segregated. So people are also, now we can also not only see that, we can do quantitatively how the oxygen carbon is. For example, you can see in a small region here of the order of around 20 nanometers that carbon is getting segregated, and there is a kind of a peak there, whereas the rest of the elements are all uniform. This kind of things, information can be out. So I can get not only a qualitative information, quantitative information about any particular phase. What is the composition of the phase at the nanometric level can be found out. Okay. And whenever you have small clusters inside a material, we can easily see. Many of us know when you are talking about glasses, metallic glasses, for example, or any glasses have a short range order, we say. Okay, what is the composition of the short range order? If one wants to find out, he can easily find out using this particular technique. Okay, and one wants to also know, there may be some materials where at the grain boundary a particular element is getting segregated. This is a particular material which is a magnetic material exclusively prepared for certain application, where you have a sodium and potassium. People wanted to see whether there is a segregation of that, and they found that there is exactly a segregation of these elements at the grain boundary. All this can be done, and variety of materials can be studied. I just wanted to give you a glimpse of what kind of materials can be studied. I divided it into two groups. One, we call it as structural materials, where we are concerned about high strength, high toughness, and things like that. So such things like high strength steels, alloys such as aluminum alloys, magnesium alloys, titanium alloys, any type of alloys you can put in, any material where you can prepare a tip. I cannot put a liquid into atom probe and study. Okay, anything that is a solid, a liquid, if I can freeze it into a solid and it can be retained in a solid state at around 40 Kelvin. Because please also remember, in the atom probe, in order to ensure the atoms do not move from their original positions, we cool the sample to about 40 Kelvin. So the chamber that you use in the atom probe, the sample tip is always cooled to about 40 Kelvin. At that particular 40 Kelvin, we freeze all the atoms so that where exactly which atom is sitting, we will be able to know. So like that, you can have variety of materials, including some oxide materials can be seen without any difficulty. And a variety of functional materials, batteries, ferroelectric materials, multiferroic materials, you name it, magnetic materials, carbon nanotubes, okay, and variety of them people are catalysis, for example, core shell nanoparticles people are preparing. So only thing is that you need to do is, can I prepare a sharp tip out of a sample? Okay, if you have a sharp tip out of any sample, in principle, any sample can be converted. Wherever you have a small sample, extremely, let's say I have a nanoparticle of about 5 nanometer. What we do is we typically put that nanoparticle on the tip of a sample, okay, glue it, and then sharpen that nanoparticle in such a way that it is a very sharp tip, and then put it into the atom probe. So this way we can see any type of materials, a large number of groups inside the country, and even some of them are outside. For example, one of that steel that I showed you was a gentleman coming from South Africa. He wanted to use our atom probe. There are people from outside the country also are coming and using. And in principle, anybody can approach various zones we have created within the country. Each of the partner institution takes care of one zone. You simply have to write to the zone in which you are located. And if you go to our website, just go to Google and put NFAPT, National Facility for Atom Probe Tomography. You will get the website. There is a small proposal form where you have to fill in. You have to tell, why do I want to use atom probe? Once you can say that, and there will be somebody who looks at that particular proposal, and once it is approved, your sample can be put into it and can be done very easily. So with that, I think I would like to thank you. And if you have any questions, I would be able to take up, provided there is time. I don't know whether I have eaten into somebody else's time. I think 30 minutes was what was given to me. So if there are any quick questions, feel free to ask.
Thank you very much for your excellent informative lecture, Professor. Now it's time for you to answer 2 or 3 questions because
Feel free, please.
Yeah, you're running out of time. Can you see those questions in your chat box, Professor? No.
Let me see.
No.
Dear participants, you can kindly unmute yourself and you can ask few questions, please.
Hello. Hello.
Yes.
Speaking, sir. Good morning.
Good morning.
Can you hear me, sir? Can you hear me, sir?
I'm able to hear you. Please ask your question.
Sir, nice presentation. I want to know what is the resolution in atomic probe microscopy, sir?
Yeah, it's like an angstrom.
What, sir?
It is like an angstrom. You can take it as roughly 1 angstrom.
Roughly 1 angstrom, sir.
1 angstrom. That is the kind of resolution that we talk about.
Oh.
To be honest with you, there is a difference here. In a typical microscope, we talk of resolution. Here, it is more as a spectroscope rather than a microscope. Our interest here is to see where which element is sitting. So we can say it is a spectroscope at the atomic scale rather than calling it as a microscope. That is the difference.
Okay, sir. Thank you, sir. Thank you.
Thank you.
Dear participants, if you have any questions, kindly share with us, please.
And no more questions? Okay, thank you very much, friends. Daniel, thank you very much. I don't know whether Tiju is there. Balakumar Garu, I have not seen him, but good friend of mine from my Madras days. So I wish all the best for you, your program, wonderful program that you are organizing. And I'm sure everybody will get benefited by this particular program.
Professor, excuse me, there is one more question I would like to
please.
on behalf of the participant. What is the cost of preparing sample and how much you charge for the
usually atom probe is expensive, I do agree. So the charge that we talk about it is in terms of a slot. We don't talk about per sample or something like that. So we talk about one slot. One slot is 8 hours of preparing the sample. Okay, 8 hours of atom probe. Okay, and also 4 hours of analysis. This whole 20 hours put together is charged about 30,000 per an academic institution. Okay, and in that particular time, we may be able to do one sample, we may be able to do more samples, depending on what is the nature of the sample. Certain samples need very careful preparation. Certain samples are very easy to prepare. So I may be able to prepare 2-3 samples in the same, and certain samples, even within 1 hour, enough data can be collected that I may be able to get a lot of information. Certain samples I may have to spend more time. So we do it as a slot. That the reason is we have 3 operators coming in each of the slots. So one shift, that is how we say shift charge. This is almost like 30,000 per shift. Okay, that includes, as I told you, 8 hours of fibbing, 8 hours of atom probe, and 4 hours of analysis. Because that analysis also has to be done by our people, because you need special softwares for this, and these softwares itself will cost you minimum 50 lakhs. Okay, so we cannot share that software with everybody. Okay, that is exclusive. You have to have what is called AMC for that. So that is there on our computers. So we will be able to analyze and give you the data and tell you here is the information. And during this analysis and during the fibbing process. The person who is interested to get the sample done can be constantly in touch on a Skype mode or some other modes. And we usually avoid people coming to IIT Madras and getting it done, because unnecessarily it will be a time consumption for them, and also somebody has to look for accommodation, all those problems, because this is not something which can be done in 1 hour. Okay, so it needs sample preparation. Sometimes it may take a day. And so as a result, we look at things. We suggest that you send a sample and then be in touch constantly on a WhatsApp mode or whatever mode and do it. How do we prepare a sample? Somebody is asking for a composite. Any sample, you have a TiO2 graphene composite, no problem. Okay, you have to identify which region is of your interest. Once you identify which region is of your interest, you can go to a fib and put the sample into the SEM and identify the region. So that's what people ask people, tell us which region is of your interest. And while starting the fib, we will ask them to start seeing the region where we start cutting the sample. And all this is done in a constant dialogue between the operator and the user. Okay. And we don't have any internship programs. This is not something which can be done very easily. At the moment, we have not thought about it. We have been training our own PhD students right now, because this is needs at least a minimum of 3 months of very careful learning. So right now it is not there. We want possibly after about 2-3 years of delivering something, we can start taking up the outside. So for in each institution, whichever is a partner institution, we defined as a partner institution, an institution which has paid around 2 crores to us, we called it as a partner institution. And that partner institution, each of the partner institution, we train about 2-3 people there. And that's how regularly they keep coming every 6 months and stay with us for some period, and they are trained and then sent back. Okay. Thank you then. You can send me an email if you have any further queries anytime. I can be happy to answer. Okay. Thank you.
Thank you very much.
Thank you, Daniel.
Professor Murthy. Above all, it's nice and excellent lecture. Thanks for your time and accepted our invitation.
Sure.
It is my pleasure to thank one of the renowned scientists in the world, and above all, is a good view. Thank you very much, Professor.
Thank you, Daniel. Bye.
Dear participants, kindly wait. The second speaker, Professor Dr. S. Balakumar, Professor and Director, National Center for Nanoscience and Nanotechnology, University of Madras, is logging in, is preparing his presentation to be visible for all. Kindly wait for a few seconds. Thank you. The second speaker, Professor Dr. S. Balakumar, Professor and Director, National Center for Nanoscience and Technology, University of Madras, is currently logging in. He will share the presentation soon. Kindly wait. Thank you.
Excuse me, sir. Hello, sir. Do you hear me?
Yes, sir. Solunga, sir.
Sir, I am from Koilpatti, GVN College, Venkateshan. Will you share this presentation through our email?
Yes, sir. Actually, we will take a note of all the participants who have registered for this today event. We will collect the mail ID, sir. With the permission of the speakers, we will try to share the content after the event, sir.
Because I think I am not able to presentation, I think, for me.
Okay.
Thank you, sir. Thank
We
you.
will discuss with our organizing team, and also we will discuss with our speakers, and we will share it accordingly, sir.
Thank you, sir. Thank you very much.
Thank you.
Hello.
அதை நான் ஆக்கி விட்டு விட்டுற அது பாட்டு கத்திக்கிட்டு இருந்து
I welcome Professor S. Balakumar, Director of the Center for Nanoscience and Technology, University of Madras. After his PhD, he did his 4 years of postdoctoral experience at Hong Kong, and NES Singapore. He was awarded a STF fellowship in Japan in 2001, JSPS fellowship in Japan 2000, and CSCR research fellowship to carry out his PhD in the year 1994. So far, he has guided 13 PhDs. There are 10 research scholars pursuing their PhD under his supervision, and one postdoctoral fellow. He has published around 240 research articles. He has 8 patents, 2 of them are filed. 6 of the Indian patents are filed and in the process. He is an associate editor in chemical papers of Springer publication, and also he was an associate editor in RSC Advance from the year 2015 to 2017. With these few words, I would like to request Professor S. Balakumar to take over the session. Over to you, Professor.
Thank you very much. Also, I thank Dr. Daniel for his great work. Sir, good morning, sir. Both of them. Daniel, can you hear me? Hello? Hello?
Little bit more audio is better. Little bit sound.
Hello?
Yeah, this is fine.
Right?
Go ahead.
So, the slides, you can see the slides? Hello? Daniel, can you see my slide?
No, sir. Actually, please click the third button, share content.
Third button. Okay, share content. Okay.
And from this, you select the application and you can open the PPT file, sir, please. You can keep the presentation in the full screen mode. Yes, sir.
Now you can see the slide.
You can keep the full screen mode, sir, please. Yes, sir. Now you can start presenting, sir.
Yeah, thank you very much. And the title of my lecture is Biofunctional Nanomaterials, and I am from University of Madras. And then the outline of the talk is this. I'm going to just give a salute to our ancient Indian doctors and also discuss on the functional material. And the topics are, there are a few topics I have chosen. Depend upon the timing, I'll cover my topics. And then we all know that, there are there were very good ancient doctors. One of them is Ashwada, and he's called as father of medicine and father of surgery, and he's the first person who did the cataract surgery as well as the plastic surgery. After that, there were many Ayurveda doctors. So one of the known person is Saraka, because he's also one is the principal of the principal contributor to Ayurveda. He written many books, and we should remember these doctors in this time. Very important. The another person we supposed to remember is Boger, who is the one who made a functional material, biofunctional material. This is none other than gold, or gold, and there are many other materials. The many other material, for example, they have he made a statue with 9 poison medicine, and it's an amalgam of 9 poisonous substance in the form of medicine. And there are 2 such statues in Tamil Nadu. One is in Palani, another one is in Kodaikanal, and both of them are made up of these kind of functional material. So functional material and biomaterial and nanomaterial are not new. It is already in our medicinal system. And then the role of nano, because we all know that nanomaterials are very high surface area. I think you must have learned a lot of students and and all of us learned a lot on nano. But the role of nano in this medicine is huge, and it is used for not only it is used for diagnostics, starting from imaging, and also for detecting the devices, and also for sensing your all kind of gases and then other things in your body, and also for as a drug carrier it is being used for sustainable release, and also as a drug carrier. And therapeutic point, there are many applications are there. There is some of them are it is used for killing the bacteria and viruses, and repair the hard and soft tissues, and all other, it is used being used in all other possible avenues. And we are going to talk about few of those things here. And before that, we should know what are materials and what are functional materials. We know that the matters in the universe are materials, and materials are different types. You can say active and passive. When we say passive material, they won't respond to any stimuli. But when the material respond to an external stimuli, it is called as functional material. And if it does more than one function, we say these materials are very smart. And then, so there are even biomaterials, there are many functional materials of that. That's what we are going to discuss. So, to understand further on a functional material, I think there are few examples here. One is on an electronic paper done at MIT, and it can change that material coated on the paper. It can change the content on every day. And another thing is our NEMS and MEMS. NEMS and MEMS are used for this kind of ceramics are used in our vehicles, electrical vehicle and electronic devices, as well as in very big structures for for sensing many parameters. And another very good example for functional material, even common people can understand that whatever the glasses that we are wearing, sometimes they have changed the color with the bright light and then dark light. So that is basically an electrochromic property or different other optical property. These kind of windows are being used in your flat, even flight windows and other other tall buildings, and wherever they require these kind of applications. So these are here. If you look into these, material does function, not the product. So if you look at the classification, it is classified based on the properties. So it is here that they are classified into three types: type 1, type 2, type 3. Energy, one is for energy conversion, phase change, also depend upon an external stimulus. It can be classified. Application wise, there are many different types of application: mechatronics, energy, and general, and that's biomedical. We are going to talk about biomedical, the material used for drug carrier and dental and ophthalmological applications. So again, the question is that I want to make it very clear to the young audience that what is the difference between functional and smart? A functional is able to substitute an entire more complex device composed of several parts. So for example, a material can substitute for a product. So because that means the material can do same as a product, we can say functional. The material able to respond to different stimuli. For example, the material responds to the pressure, the temperature, the thermal parameter, respond to all other few other parameters. That is, the same material does more functions. So that means we can say that materials are smart, or now we call it as nano. Always we say food itself a medicine. So when you say food is a medicine, so the quantity should be less. You can increase the surface area. That time food also can be a medicine. So, but there are another way to define the medicine and nanomedicine. Nanomedicine is the materials or the medicine used to monitor, repair, construction, and the human biological system at the molecule down to the level of molecule using engineered nano device and nanostructures. So that nanostructures, that is what we are going to discuss here. And one of the other major application, the focused application is a nanotherapeutic material. The therapeutic materials are you can design and synthesize, and you can use it for, as we discussed earlier, you can use it for diagnostic and therapy of the molecule. This is a new terminology, relatively new terminology, which is being used, and there are most 150 companies already developed, and this more than 36 products already available in the market. More than that, so it is that area. Therapeutic and nanofunctional medicines are not new. So this is one example that everyone can understand. Here this molecule is a functional molecule. You can see there are many different layers. In the right side you can say it's an imaging agent, you have it. And the other thing is when you want to target a specific molecule, you can have that molecule. And similarly, you can combine with a biocompatible polymer and the cell-penetrating agent. You can attach more than one drug, and what time you want to drug, where you want to drug, accordingly you have to give a similar. So these kind of molecules can be used for many applications for to treating the devices. So it is design and the synthesis of material is in the hand of material scientists or organic chemists or nanoscience people. Okay, then this is another example which you can further make it very clear. You can see it is one of the copy of the book from the patent from the lyric. So here you can show 6-7 layers. Each one is a nano material. Some of them may be a layer. The core material may be the core may be a spherical particle. So the first material used for cells when you want to send this material for a treatment, first you have to target your cell, which cell you are. So this is the first material used for that. Once you reach the cellular, your cell, then you have to look at the you need the right material to probe the to get into the cell. It's called intracellular targeting. Third one is when you enter the cell, you have to sense it. So whatever you want, for example, if it's a cancer, your calcium content will be more. Calcium that is biomolecules can be sensed or any other molecule, then you can go for a treating or delivery. So that is the last part will give you the delivery. So before delivery, you have to sense it. Before sense it, you have to go to intracellular. So this is called it is a guided targeting. And a targeted delivery, and then targeted and you are targeting the cell, and also you are sensing the one, and then third one is you are delivering. These kind of a multifunctional material can be developed with the help of nanomaterial. So that materials also can be used for not only used for your diagnostics, it is also used for therapy. Here just one material we all know, there's an iron oxide or gadolinium complex agent. It is used for MRI. MRI is magnetic resonance imaging, where you want to which this MRI want to use it for. You can it is image your brain cells. Very small. It's down to the level of atom. You can imagine there. Some say due to your water content in the brain, it may not be. You get a clear picture. We use an iron oxide as your magnetic material as a contrast agent. You can also get an optical image if you combine with an quantum dot, that is called the magnetic quantum dot, and also similarly these materials can be used for treating treating your cancer, the iron oxide. So that means this material can do more than one function. This is another example. So the third part, which is I just want to elaborate, because this is an area which we are working, is called biofunctional material for heart tissue, that is tissue engineering application. For example, if you see here, this body has, you can see that there are many places we have an hard material, external material to support the system. For example, if you have a problem with your bone or knee bone or your heart valve or your eye, so we have been using this material to support the system, are using the material to extend the lifetime of the system. This is being done. These materials are called biomaterial, or I would say that the exact definition is non-living material used in medical device and designed to interact with the biological systems, or we call it as a biomaterial. Or it can be any substance or combination of more than one substance, but it should be other than that. It can be synthetic or natural. It can be used for any period of time. It can be used for a week or for a year or for your lifetime, which augment or replace partially or totally any tissue or organ or function of a body in order to maintain or improve the quality of the life of the individual. Then this material is called biomaterial, but there are three different generations. In 1980s, these materials are only used as an inert material. Do not trigger any reaction. It is neither rejected nor recognized. No recognition. Do not bring any good result also. You have to, you have to keep on monitoring. Second generation, they want to make this material, compatible with the system. So they have coated with it. The coating materials are called as bioactive material. Ensure more stable performance in a longer time and for a period that we are required. Third one is biodegradable. They have come out with a material, which material can be converted into body or converted to tissue. Correct? The material should be biocompatible, bioactive, and that should be it have a chemically degraded and decomposed by natural effectors. These materials are called biodegradable. Now we are working on third generation. Actually, we are working on fourth generation using this bioactive material, and with the proper design. We are in the fourth generation. I think we are working on innovative material. That is our innovative material for biomaterial. That is how we can classify it. So in our lab, we have started this work for the past almost, we started in 2011, and we worked with the bioactive glass, and then we synthesized this material. Then we moved with, design and fabricate the scaffold. Then we combined with the metal oxide and the PMMA and RGB to increase the mechanical property and for, for coating application. We also incorporated antibacterial silver to improve the antibacterial effect. Then we work with, not to parallelly work with HAP and iron oxide, and also we combined with your Siddha material. It's then, as of now, for the past 3 years, we are working towards application, product for application, that we have developed a coating material for your dental caries. Another also we have used this material for in IDCAR, to coat this material in a water container and an anti-corrosive coating. Third one is we also used for this for ophthalmology. We are working with Shankar Netralia and we can make a corneal membrane. Then right now we are working on a chemostat within Bayrak Pandit. This is this is our work what we have done. I'm going to explain for next 20 minutes on what we have done and also this one. So these kind of material we started as a functional material. Now we have moved to another era. Another area is called the multifunctional. When you say multifunctional, if you look at this animal has aggressive animal has a 3 different phase. So when we have a 3 different phase, that is basically you have to design and synthesize a material design and synthesize a material in order to have a design, you should have a better control on the structure and function and the architecture and the composition to make this material workable, right? So that materials. So what we have chosen here, and just another slide. You have these are some of the materials: tricalcium phosphate, and then HAP nanofiber and bioactive glass. And these materials can be used as an implantable material, and also it is coated on your implants for bone regeneration or bioactive. And also you can enhance the surface coating to make the material active. And also it can be used for drug delivery and the cancer therapy and gene therapy. These are the proposed or projected are the materials presently used in various forms for very different applications for this kind of inorganic materials. So, but many of us we are using so many elements. Is it compatible to our body? Our body has a lot of elements in our body, and starting from you can see the oxygen, your carbon, oxygen, hydrogen content, and also there are trace of elements. You have almost many common elements are there in the body. So you have to make sure that the material is compatible and is not adding the more content to the body. So when you talk about when you come back to the next stage, so we are working on the material for heart tissue. There are 2 different heart tissue in body. One is bone and the teeth. So in often nowadays we are going for surgery due to your accident, osteoporosis issue, or your dental caries. So these are happening. But if you look at the statistics, it is being increased, tremendously. So, but now the recent charts are it shows this nature of your teeth issues is depend upon where you live and what kind of food you are taking, of water that you are taking. If you look at here, this is health commission long back, but it shows the trend that dental caries were more in Chennai and Hyderabad. So that means that is some of the element in the water or contaminate water of your food system, your affect your dental caries. So what kind of surgery is being done? For example, for bone, see any surgery, if you have an accident and they put some implant in your body, that implant may be there for some time, and after that your body keeps changing. Your bone system also gets changing. Definitely, this whatever the material implant in it will not adapt. So it is necessarily we are going for a second surgery. So that's so called revision of surgery. The revision of surgery statistics is increasing, which they have shown here. It's a very long one, but the trend is the same because it's shown up to 2030. So the surgery is increasing with, for example, hip surgery and knee surgeries are increasing with the increasing time. So again, coming back to the material, your bone and the teeth is made up. Bone and teeth are generally we call it as composite. It's a natural composite. It's a composition of polymer on the nanocrystals of hydroxyapatite. So it is known that our systems are also made up of nanomaterial. The nanomaterials are in the shape of crystalline, and they are not a single material, they are composite. And similarly, your teeth is a beautiful structure. It has an enamel, it has a tentin, it has a bulb, and it has an alveolar bone, but everywhere you have a calcium phosphate. We will discuss it in this. So the exact composition, your composition is that if composition of 60% inorganic material, 25% organic, and type 1 collagen, 15% water. But truth, you see, it is 90% hydroxyapatite. 10% also it varies with the layer. That structure and the composition. So you come back to the hydroxyapatite. Hydroxyapatite is a naturally, it's a mineral. It's a calcium phosphate, and 69% of bone has hydroxyapatite. It is also called biological apatite, and there are different names are there: fluoroapatite, chloroapatite, and carbonate. And when you prepare in a nano form, the reactivity is good, and particularly it improves cell adhesion, cell differentiation, cell proliferation, cell osseointegration. So now we are taking the advantage of nano. We are modifying this material, or designing the material, synthesized in a required form, as a required composition. We are using this as a for tissue generation or tissue engineering. Correct. So there are already this material is not new to the market. In micro form, it is already used for ortho, and also for different blocks are used, and gel form it is used, and then for there are many forms it is scaffold is being used. So where it can be used, it can be used for bone graft filling, and used for coating, and also used for in the interfaces. Also it is scaffold based, used for the tissue, the regeneration of tissue. It can be used in different forms. So in our lab, we have synthesized this material using very wet chemical approaches in the beginning. And then we, in order to enhance the mechanical property, we introduce an alumina and also graphene. And then we look at the mechanical property and the corrosion resistance implant jointly with other two departments, also with IGCAR. Then we also work with not synthesis osteoblast cells, we combine with iron, but the point is we use the micro synthesis to get a nanomaterial and see the properties. And similarly, we work with we fabricated a few scaffolds with the CMMA and evolved for bone generation application. And for bones up to recently, the sulfates have been introduced because it is good for your bone regenerative applications. So, but nano has a certain limitation. The clinical applicability is a lack of all the biometal has these issues and mechanical strength. Another thing is that this is since in highly crystalline material, the release of calcium phosphate ion is not easy. So you need to modify the material and also mechanically improve it, and you have to increase the flexibility of this material with the help of nano. The material comes in that after that it is bioglass. Bioglass is basically an amorphous material, amorphous silica, in which you have a crystalline sodium calcium phosphate ion in specific proportion. There are two types, depend upon the composition application, and he has come out with many different compositions, and we used for application. This is one of the highly integrated material. It is also can be used for dentistry to fabricate your pulp tendon regeneration, for implant coating, for hemostat. Similarly, it can be used for bone graft and scaffold, and these materials also already used in nano form for bone cancer in osteosarcoma treatment and hyperthermia. So this is possible, but how do we synthesize? What kind of methodology you can adapt? Also interesting one. So these are some of the available one. These are implant scaffolds are there. This made up of hydrogel, and it is in mesoporous NPG, and then drug delivery vehicle, and also your nano vaccines. It is an injectable one, and also it can be used to mesoporous scaffold they have fabricated. It has a earlier mentioned it can be used for cancer, hyperthermia treatment. So, but the advantage of nano is we have to look at that. This can be used. It can be used when nano level. This is since your surface area and the bioactivity is increasing. You need this can be used. This application of this can be extended for other application, enhanced for present application. But depend upon the technique that you are using it or your requirement, you can design and synthesize the material. That means the required property, you can make a product out of this. So this is a known. So such materials, it is not only used for dentistry, also used for ortho and ophthalmology and drug delivery. In particularly, this kind of functional material in orthopedic, you can go for scaffold and implant coating, and implant as a filler material and the coating. Dentistry, you can use it for tissue regeneration, dental pulp regeneration, and also stop to blood clotting application, and also for PDL layer and alveolar bone regeneration. And ophthalmology, it can be used for drug delivery, it can be used for ophthalmology related bone application and the corneal membrane disease and the cancer, it can be used. This is the versatility of this bioactive functional material. So this is some of the material that is already in the market, in the bioactive material. It is all exists in different form. It is already being used in sensor in paste. It is a Novamine, and there are many products are available, but they are all used in micro form. So what we have done? So why nano? Nano is, see, for example, this when the size reduces, protein absorption is good, and the cell adhesion specific capacity is increased, cell proliferation is enhanced, so cell differentiation is enforced because of your, this is higher surface area, biocompatible better than your microparticle, osteoblast adhesion is improved, and stimulate the surface topography of the bone. So that is an advantage of this material. So we have generated many different, these are all nano structures developed in our lab. Your different particles, physical particle, mat and fiber and the core shells and the cubes and the nano sheets and the hollow wires and the blanket and the sheet and with many different morphologies, shaped materials are to the crystalline materials also we have synthesized. And some of the work that is the recent work is we have used, as a material scientist, we want to see the role of the nano structure and the morphology on the application. So when we change your crystallinity, that means you are changing the shape of the material. Certainly, that a very good impact on the property. One of the property we can see the hemocompatibility. The hemocompatibility is good for the material prepared at certain condition because the surface area is different. But if you prepare at the higher temperature, the morphology changes. There your surface area is different. But bioactivity is good. Now you have to compromise it. Which one you want? Do you want to have a very good bioactive or biocompatible? You can trade off. So that means based on your requirement, you can choose the morphology and you can choose the process condition. You can get the material. So we also look at the cell proliferation is the biocompatibility is good. It is your fluorescence image clearly exhibited there. That is one work. Another work what we have used is we have used a different kind of an annealing, a different kind of a material synthesis. So the idea is to break the molecule, to increase the surface area, to maintain the morphology. We used probe conication to get a homogeneity particle, and as usual as a microwave particle to do a quick annealing. So there is a change in the morphology. You can see these are all the morphologies are different. The shape of the different and size of the particles are different. So the hemocompatibility is different. Your surface area is different, and your the pore diameter changes. So this is when we develop the sol gel method, and then we talk about your annealing condition, and then your probe conication, what kind of annealing you have done, and how do you change and size and the mesoporous material, how you can make product out of it. This is the second stage what we have done it, and then the later we use this material for dentistry application. Again, I am when you come back to the structure of the tooth. The tooth here, I just want to take 1 minute to discuss here. The tooth is here. The top one is an enamel structure. These also this 90% calcium phosphate. Dentin here 85% you have a calcium phosphate. Then there is a periodontal ligament region, and then cementum, alveolar bone. But everywhere you have a calcium phosphate. The beauty of the creator one is that it has a different beautiful structure, and the calcium phosphate you have a gradient is there. So gradient tells you the function, changes the function, and also the strength and then application of this material. So such things, such a beautiful structure, it is easy. It's very difficult to regenerate all the structure and protect it, right? Okay, enamel is the hardest component in the body. It is very difficult. It is not possible to reverse it. Only thing is, if there is a problem with an enamel, you can use these kind of a functional material and you can protect it. So one of the main issue we all known as a dental caries. It's a prevalent into one of the chronic devices, I mean, chronic disease, oral disease. It's just because of the bacteria and your water content. So here, if you treat with the right material called active material, for example, because you need the more amount of scandium, and also sometimes they use magnesium and they should use to treat, to regenerate, so even they use silver. So dental caries can be found to be lower in the way. So it is known that scandium is one of the very important components. So we have developed a material with the scandium component. This is one of my student work, Dr. Durga, and we published this in biomaterial science. So she has developed with the scandium incorporated nanobioglass, and he worked with an Ramchandra Medical College. And we see that when you open your, when you polish your teeth, you can see that your 10 tubules are open. But you brush with your scandium calcium powder 5 minutes every day or 3 minutes every day, is completely closed. The closing, because the closing is called tubule occlusion capacity. The tubule occlusion capacity increases with increase of scandium content up to 15%, and that 15% is enough to regenerate, to completely close your tendon tubule. That means you take care of your tendon, and then take care of tendon, and also it is good. Also, you can protect your the remaining enamel and close the as a cap. So this is one of the application of this material, potential application of this material. It is not only you can use it as this material, it is also possible to come out with some of the products. It can be used for synthetic polymer and it can be used for hydrogel. So what we have done is we are targeting for hydrogel and hemostat. And here I am showing that another student work. He has take the same bioglass and mix with the sodium alginate and also gelatin. She fabricated a lyophilized sheet. It's a nano membrane, two-dimensional membrane. That membrane we use for many different applications, starting from for tissue. We are evaluating it for tissue generation and also for hemostat application. And similarly, the other student, he also developed a bioglass and he evaluated the hemostat application. This is one of the potential hemostat material, and this is your control of your how the blood cells are changing with the structure. So this the lie your hemo within a few seconds it can freeze your blood. So this is based on this work only. Recently we got a project from Biovac to develop a better hemostat. So this is a snapshot of that kind of work. We developed beads using material and also scaffold using material. Presently, we have developed, it is you can say it is a designed scaffold, and using our tooth socket model, we have developed it. So right now it is already in the another stage, and since it's a running project, I cannot share much data on this. It's our preliminary work. So hemostat is coming up. Then we also work on calcium fluoride. So calcium fluoride incorporate bioglass. Generally, we know that fluoride is the content, it should be required for that. Fluorine is very important. So we incorporate the fluorine and we look at the mineralization and the structural aspect and the mineralization aspect, the biocompatibility and we found that 10 to 15% of calcium fluoride substitution enhance the properties of this material. So, and then similarly, we work with the SRM Central College, and then they are help us to do the tentin remineralization of calcium fluoride bioglass, and it shows that, and this is the interface. This is a tentin, and this is your material. But you can see that this control is a very good sharp interface. Since you are PG treated, there is a development in your region. You can see that the growth in the junction is just a remineralization occurs. So that is also another additional picture shows the structure of the grown your teeth. This is we took from the with appropriate approval they have done with the human teeth. So that is shown. And similarly, another material we have developed is a bioglass, copper bioglass, the filling efficiency of bioglass. We have developed this material, and they have treated this material make pellet and powder and the silicon, and they are studying the penetration. They are studying the penetration using the dyes, and it is being developed in the upcoming work. And similarly, we have developed this material with Bayan, or it is a Sauber method. They have developed Bayan iron oxide. It's a composite which can be, it is a magnetic. The bioactive material is not a magnetic material. When you combine an ion and ion in nano form, in the core shell form, it is a highly super paramagnetic material. It is used to already we are trying it for hyperthermia application. So another next 5 minutes I'll take for what we have done with ophthalmology. This is one of the joint work what we have done with Shankar Nanomaterials High Hospital. And in general, they have these materials are already used for, they are using for regeneration of bone in your eye region, and also for keratoprosthesis. They are using for artificial hair. They are drying with a hard material. Nowadays, they are trying to reduce the structure and the thickness and then flexibility. They are using, they propose to use a bioactive glass, a stainless template, and the corresponding with the bioactive glasses is shown here. So what? And so in our idea is to develop such a material and suitable, because the composition of the metal is very important and the structure of the metal is very important. Then only you can easily design it. That material for. So what we have done is we have developed this bioactive metal with different composition, and we managed to develop a single phase compound along with the silica. So this material is a highly active material, and we evaluate this material at Shankar Nanomaterials with cell culture studies, highly suitable. Then we work towards developing the corneal membrane. So this is a corneal membrane developed in our lab, and that material can be the corneal membrane. If you use a proper dye, we have managed to control the transparency 95%, and your thickness and then shape. Everything we managed to reproduce it, and this is the one. And then you can see the transparency is very good. This is the nature light, and we vary the composition. We found that this is highly compatible, cytocompatible, and also optical transparency is good. So then degradation behavior also we have studied. So we found that there is if it is a degradable, it is used for different applications. If it is non-degradable, we can use it for corneal application. So if it is degradable, you can use it for you can drug delivery vehicles. That's what we have done it, and that's what we have. This is what these are some of the application of the known hydroxyapatite and the bioactive material that we have used. We develop and we check the functionality, and we are moving towards the product. So these are some of our publications from this work what we have developed, and this is my team. And Dr. Durga is the one who started this work, and Dr. Rajati is our collaborator, and is from Department of Biophysics, and these are all 6 students presently completed their work, and Rishi is working on with Shankar Nanomaterials from our project. So, and I thank these students at this time, and really a wonderful one. And also I would like to thank my collaborators, Dr. Ganesh Venkatraman from Ramchandra, and Shankar Neta, Dr. Krishna Kumar, and Dr. Ramya from SRM Central for their collaborators. And I also thank DPT and BIRAC, and also DAE, IUT, CRS for the funding. So thank you very much. And now this session is open to questions. So Dr. Daniel can take over. Hello.
Thank you very much, Professor Balakumar. It was a wonderful lecture to know about the bone and health, how the nanomaterial can be utilized for the applications in those particular area. Now the session is open for the participants to pose the questions to the speaker.
Hello.
Hello.
Hello, sir. I am Navneet from Amrita University.
Navneet from?
Amrita University, sir, Coimbatore.
Yes, sir.
Yes. Sir, my question is, I have seen characterization techniques like MTTS for ensuring the biocompatibility of the material. MTTS.
Okay.
Is there any simple way to characterize a material if it is a biocompatible or not to ensure?
But
MTTS will take 48.
Very simple. See, there are many ways to look. It depends upon what kind of application that you are looking for. Right? Biocompatibility. What is the material that you are using, and where you want to check biocompatibility? Here, I have shown the biocompatibility studies also. See, where you want to do it in cell level, you have to use the cell lines. Correct?
Like for making a prototype, like for implantable device.
See, when you want to use a system for human, you have to use the mostly first you look at your hemocompatibility. You can use the blood. Another you can do the cell compatibility. Third you can go for MTTSA. Right? There are many tests. Testing you have to look at the where you want to use it. What is the right methodology? There are many, plenty.
Is there any primary technique to ensure? Because these MTTSA
in my lab, I know it is with an appropriate approach. First you check the hemocompatibility.
Okay, sir. Okay, thank you.
You can use your own blood or donor's blood.
Okay.
Right.
Professor Balakumar, there is another question. It
Yes,
says
sir.
that explain the chemical toxicity of all these bioglasses.
Okay.
Professor, explain the biotoxicity of all these bioglasses. There is another question in the chat box.
Okay. Toxicity, whatever the material that you are taking in your body, it will have a toxicity. Correct? But relatively compared to all the material, biomaterial has a very less toxicity, because it is whatever the element in it is already inside your body. And then this material is highly degradable and easily absorbable. So then obviously the toxicity will reduce. But that is the reason you can use this material in a bulk form as a filler material, as a supporting system. It is possible to use it. Hello?
Sir, can you please tell about IC50 value?
What is that? I don't have that
IC50
number.
value.
No, I don't have that number. Maybe I can. You can just email me. I can give you the data.
Okay.
So there is another question in the chat box. What are the ways to functionalize the biomolecules? Is there any standard methods? What are the ways to functionalize the biomolecules?
See, functionalization is depend upon again. See, everything is a specific one. So when you want to say that I want to functionalize it for what application? If I functionalize it for drug delivery, use an appropriate organic molecule to functionalize it. Correct? But here what we are using is for heart tissue application. Here, do you need a functionalization first of all? If required, yes, you use to do it with some organic chemistry. Hello? Hello?
Yeah, Professor, thank you very much for your answer. There is another question from Dr. Raju Nandakumar Karunya, University. Over the years, these nanomaterials change their shape and size due to external stimuli like heat, light, etc.
Okay.
So the properties change. Hence, its effect on human health and environment. What do you think?
No. See, these are all high temperature materials. High temperature materials, it will not just dissolve with your body temperature. Body temperature, it is only there the slow release of ion. So that the releasing rate and absorption rate may be almost equal. That's a little bit bigger and there. So it will be absorbed. So whatever the condition, this material is designed for the compatible material for your biological conditions. There is no issue with that.
Yeah, if there is no question, I thank Professor S. Balakumar for his wonderful lecture. Thank you, Professor. Professor B.S. Murthy conveyed his regards to you, and he recollected his old memories at Chennai.
Thank you.
Yeah, thank you very much, sir.
Thank you, sir. Yeah, I think Professor Piji is in already. Yeah, thank you.
Thank you, participants. Now, the third speaker is from IIT Madras, Professor Tiju Thomas, Associate Professor, Department of Metallurgical and Material Science. Now I request co-convener Dr. P. Murthy to introduce Tiju Thomas to the participants. Thank you. Good morning, Tiju. Tiju, are you online?
I'm online. Are you able to hear me?
Yeah, right now. Thank you very much for accepting our invitation.
You're very welcome, sir.
Yeah, now Murthy will introduce Dr. Tiju Thomas.
Good morning to all. I am very much happy to introduce the third speaker of this session, Professor Dr. Tiju Thomas. He is a Associate Professor of Interdisciplinary Program at Department of Metallurgical and Materials Engineering, IIT Chennai, and he is also the head of Applied Nanostructure Engineering and Nanochemistry Lab. Dr. Tiju Thomas, he had his PhD from Cornell University, and later on he had his postdoctoral at University of Toronto and Memorial University of Newfoundland. Professor Tiju Thomas' research areas are nanomaterials for energy and environmental engineering, computational materials engineering, complex ceramics, compound semiconductors. Professor Tiju Thomas, he has awarded from Fast Track Young Scientist Award and Inspire Faculty Award. With this short introduction, I request Tiju Thomas to share his presentation. Thank you.
Thank you so much, Dr. Murthy. I hope all of you are able to hear me.
Yes, we can able to hear you. Dr. Tiju Thomas, please, if it's possible, you can also turn on your camera if possible.
Okay, so let me see.
That's the second button from the left.
Yeah, last time I tried, there was some instability, maybe
Oh,
because
fine.
of the bandwidth.
Then no issues. You can start presenting. Please go to the full screen mode of this presentation.
Yeah. Just a moment. Let me try my luck here. Getting this on. Yes. Hopefully now you're able to see. Oh, but then there is an instability.
Oh, this is the. I think this is a share screen option. Maybe with the share content, you go to the application, please.
No.
With the share content.
Earlier it was showing, isn't it, Murthy?
No, it was you shared the screen, but instead of sharing the screen, please go to the application, and you can start. Just click the PPT alone.
Share content and sharing the screen.
No, don't share the screen. Share the application.
One second, Murthy. I'm not able to hear you. Are you able to see this now? All of you?
Yes.
Are you able to see this now?
We got a echo.
Okay. So shall I proceed? Murthy, can you say yes?
Yeah, you can go to the full screen mode and you can start presenting, please.
Yeah. So good morning, everybody. I'm aware of SREC. I've come there a couple of times, and I'm very grateful that you have me over again, this time in the virtual space. The topic we will deal with is nitrides and nanostructures for energy and environmental applications. So I call it the energy environment nexus. And over the last few years, it's becoming more and more clear why we need to address not just the energy part, but also the environment part. And many of you here, I suspect you do not know much about my campus. So I live in what can be appropriately described as a forest. It's a beautiful place, and I really invite you all, as and when possible, maybe in the post-COVID season over here. All right. So the areas of my research are as follows. I work extensively on wide bandgap semiconductors, especially those having novel compositions. We also explore new synthesis approaches, and to understand those we use simulations, and at the same time we use those materials in device applications. So there is some the bandwidth and so on. So I think what I'll do is I'll use this in the non-full screen mode. Hope that works, because there is a delay otherwise added. So a bit about the work that's going on in the group. It's as follows. Oh, somebody said I'm not audible. Am I audible now?
Dear Tiju, the
Am I
voice
audible
is
now?
getting echoed.
Are you able to hear me now?
Yeah, now this is fine.
This is fine, no?
Yeah.
Okay. All right. So let's
Audio is
try
very
this.
clear. Audio is very clear now.
Now it's clear. Okay. So what we do in the group involves very evidently multidisciplinary activity. For example, we have been looking at water splitting for a while now. Over and above that, we have been looking at sensing-based technologies using novel organic complexes. This is something that the chemists among you might relate to a little bit more. And almost always we take an engineering approach, which is to say that we are eager to look at scalable production possibilities. And in that context, we have been looking at oxides and oxynitrides. And we also build reactors here in our campus. And increasingly, we are finding some very exciting developments in what we call the ultra small size regime, which is the 2 to 3 nanometer regime. So there are some core competencies that have been listed out here, which include air sensitive chemistries, crystal growth across length size ranges, by the way, and then low dimensional materials. And on the simulation side, we have been doing BMD, that is bond valence molecular dynamics. And increasingly, we are building an interface between BVMD and machine learning as well. So in terms of the activity, it is both national and international, having significant interactions from colleagues in similar spaces across the world. So let us begin by asking a rather simple question. Why bother with electronic properties? Because most of the oxynitrides and nitrides, the primary motivation for exploring them has to do with their unique electronic properties. And then those of you who may be in the first or second year MSc or so might wonder, why should you even consider electronic properties? What would be the use after all? Now, to highlight that, I'm giving a couple of examples here. So here is, let us say, a particle of TiO2. By the way, TiO2 is something that you might have likely consumed in your lifetime, because many pharmaceutical drugs are carried on TiO2. It is extremely inert, bioinert that is, and the pharmaceutically relevant active ingredient is added to TiO2, and it is that which is sold in the form of the tablet. So the tablet is not almost always the medicine, it is the carrier of the medicine. Similarly, TiO2 would be there in your paste, toothpaste, for instance. So this is such a TiO2, clearly scalably produced. It's an oxide. Remember, oxygen is abundantly available. And what happens to TiO2? If you go back to your high school science, or let us say your college level engineering physics or chemistry, you might recall that there is something called valence band and a conduction band. And if you shine light of the appropriate energy, then you would have electron going from the valence band to the conduction band. For those of you who have forgotten this, you might want to recall what happens in atoms, and something that you would have studied in your general chemistry, let us say. So you have hydrogen atom, which has 1s, 2s, 2p, 3s levels. And to begin with, in the ground state, you have 1s2. You shines appropriate energy of light, you will have 1s1, 2s1. So that would be the excited state. So this is the solid state analog of that. What do I mean by solid state analog? You have TiO2, which is an extended solid,
So it has energy levels. Those energy levels, by the way, are called bands. And these bands are also a little bit like the 1s2, 2s2 that we were talking about, wherein electrons are, let us say, all present here. You shine light, you can push a few of them above. All right. So I just saw Professor Gnanamurthy asking for full screen mode. So there is some issue here. When I'm putting it on full screen mode, I'm not able to go from one slide to another. All right. So it seems to be some issue with the interface between WebEx and my computer. So that seems to be the challenge. That is why I'm doing it like this. I hope you excuse me. Yeah. So next is what we are doing in this experiment is making TiO2 sit beside a carbon nanotube. A carbon nanotube is essentially graphene. By graphene, what I mean is a single layer of what would happen if you, let us say, took your pencil graphite, you know, you have a pencil, buy a pencil, strip the wood part of the pencil, and then say, okay, I need just one atomic layer of this pencil graphite. That would be a graphene, all right? And then I can roll this graphene around like this. So it looks like a cylinder on the side. Its lateral view would look like that. All right. And then if I put this TiO2 beside this, lower, and if I shine light, let's see what happens. An electron goes from the valence band to conduction band, and there is a traffic of electrons. The electron goes and jumps into SWCNT also. Now, this is interesting because what would otherwise have been in a single material, namely the electron and hole, is now separated. The electron is separated and pushed into another material, and the hole is separated and placed here in TiO2. So you can use the hole for a chemical reaction, you can use the electron for another chemical reaction. Now, this is wonderful. And why did this come about? This came about because of the fact that this electron was able to just move through seamlessly with the energy it has, move into the CNT. So the energy levels matter. Now let's take another example. This is something that is used in blind sticks. So those of you who might know visually impaired or challenged people, they walk with a stick. Now the question is, can you make that stick smart? And by smart, what do we mean? We mean something like this. So the person is trying to feel the floor, and if on the floor there is an obstruction, the person should be able to get some kind of a signal. Now, how we give that signal is a different question. But let us see if we can generate a signal at all. So here I have layer 1 on top of layer 2, and I have a deflection. Now, both of these materials, they are what are called as piezoelectric materials. When I put them together, they form what are called as bimorphs. Morph means form, bi is two. So biform similarly simply means two forms. What are the forms? Piezo 1, piezo 2. So when I deflect it, I will have, let us say, a potential difference between the top of the first one and the bottom of the first one, the top of the second and the bottom of the second. You have a series cell there. So you can in principle get a relatively good signal if you have biform, or for that matter, you could think about triform, tetraform, multiform, till you get a good enough signal that you capture. All right. Now, so you can just use something like this at the tip of this walking stick in order to generate signals which can eventually become automated and maybe even given as speech feedback to the person who is blind. So this is an interesting application, isn't it? Where does it come from? It comes from the electronic properties. Now let's look at another example. And some of you, I'm sure, come from electrical background, electronics, and so on. And in the world of electronics, you have seen the concept of the channel of a transistor, wherein you have, let us say, a gate, another gate, and then you have a channel in between. Can you think about a channel that is just made up of one or two atoms? That is what this is. These are what are called as molecular transistors. They are truly atomic scale. And what happens is that in the case of these channels, you have the behavior of the atom reflected. And what is the behavior of the atom? It is quantized. The energy of the electrons in these atoms are quantized. And by extension, you cannot pass an arbitrary amount of current from left to right. It would be in steps. You would have I1, then you will have I1 plus delta, then you will have I1 plus delta plus sigma, then I1 plus delta plus sigma plus gamma. So this would be the jumps. The delta, gamma, alpha, etc. would be the quantum jumps. So from a transistor that you have studied in your, let us say, BSc chemistry or BTech electrical engineering or electronics or information sciences or whatever, you get into an entirely new regime of devices wherein you do not have a continuum of current. You have jumps in current. By the way, for those of you who are from physics, you might have studied this in the context of something called the Coulomb blockade. Okay, so I leave you with one question here. Some of you I know are interested in battery technologies and so on. Can you use materials like this in batteries? Just think about it. Just think about it. And maybe it'll open up a new universe for you. I mean an intellectual universe, research universe. Okay, all right. So I'll move further, and this is for the chemists among you, and to make it a little bit more grounded in the sciences. So what determines electronic properties, by the way? The electronic properties are determined by ultimately the Hamiltonian, and the Hamiltonian is an eigenvalue problem. All of you are aware of it. And this was the case for the atom, this is the case for the molecule, this is the case for the solid. Now, what does this Hamiltonian have? The Hamiltonian has a potential term, and the potential reflects the arrangement of atoms in the lattice. So you can give that information and solve the problem. It is classically done by using something called self-consistent field calculations, and eventually by using suitable approximations, you can also capture real properties of materials. All right, so I leave it at this. I could go on and on about this, but in the scope of a 20-minute discussion, I would just like to give you pointers. Now, how does this connect to energy and environmental materials? Well, one way in which I can think about connecting it to energy and environmental materials is if I showed you this figure. Now, this figure is interesting. It plots the year, and 2020, this is the year we are living in. And of course, the graph would change because this was a projected graph. And it turns out that the revenue as a function of time for conventional lighting, you can see, is diminishing. For LED lighting, it is increasing. So what are these LEDs? These are light emitting devices. You have it in your home, most likely. And it turns out that they emit light the way they do primarily because of the kind of electronic properties they have. And that is why electronic structure and electronic property matters. Now let us look at the practical dimension, the practical side of it. Yeah. So the practical side of this is as follows. Now, it turns out that LEDs can help achieve a significant reduction in CO2 emissions. Really, really significant. And this has been consistently the case study after study. Now, if you look at the places where real PN junction devices are manufactured, you will find that they happen 1, 2, 3, 4, 5, 6, 7. 7 small corners of the world. The remaining are blank. Now, some of you were asking about employment opportunities. There is employment opportunity for you. If you can think about ways in which you could develop scalable production of these LEDs, then you are opening up a space for yourself, a space that is connected to LCD, LED, VFD, what are called as vacuum field devices, field emission devices, electroluminescent devices, and so on and so. So typically, these technologies would require a combination of the following skills. You would have to understand electronic properties, yes, but you would also have the ability to make thin film devices out of it. And those thin films could be made by using a wide range of techniques. I mean, there are at least 16 that are regularly found in literature. So let me show you the kind of device you could make to start your company. So if I had, let us say, a phosphor sitting inside, what is the phosphor? Phosphor is actually the light emitting material, and it is sufficiently thin, let me say 20 to 50 nanometers, not more. And it has all these engineering properties. It has good conversion efficiency, which means to say for energy I put in, I get good energy out. I have sufficient stability, thermal and chemical, and I have just the right particle size distribution that allows a very thin layer of the phosphor to be made possible here. And then I deposit a top electrode, a bottom electrode, and an electrode is usually a metal. And then I say, can I apply a potential difference, let us say a DC, across this device so that I push current, which in this particular case could be a tunneling current. This is for those of you who have taken some course in quantum mechanics or solid state or some such. Tunneling current is that which happens because of the purely quantum mechanical nature of, especially in this particular case, electrons, and it is classically forbidden. That means to say that you have a metal, it would naturally not send in an electron into this, and the electron wouldn't naturally tunnel through. But it turns out that the thickness of this is so little that for the kind of potential barrier that exists between this two materials, you still have current going through. So if you were able to make a device like this, then you could think about making a wide range of display devices. All right. So next is somebody sent me a message for annotation and I'm not able to go to the next slide. Can you just undo what you did? Okay, now it's okay. All right. So photoluminescence, I don't know the current composition of the class, so I won't go into great detail. But I mean, I'm assuming all of you remember something of your +2 or high school science. So you can imagine an atom, and let us say that this atom has energy levels that looks like this. It's atomic, okay? So it's something analogous to 1s2, 2s2, 2p, and so on and so on. Somebody says there's a lot of echo. Okay. Are you still getting a lot of echo? Okay, so Naveen Kumar says there is echo. So I'm just checking my audio connection. You're using computer for audio, it says. Do you have any suggestion, anybody?
Tiju, I have a kind suggestion. I am Murthy. Just you can you press the end screen button over there and you stop presenting your screen.
So
please stop presenting your screen.
Okay, 1 second. So I am sharing the screen, not presenting.
Yeah, don't share the screen. What I try to say is, instead of sharing the screen, while sharing, there is another mode called application. There you just you click the application and from there you select the PPT.
Okay, so I'm stopping the sharing now. Share content. I'm sorry for this technical. So where does this application come?
No, you just close the share content. There is a indication. You close the share content. Go to the WebEx platform.
Okay, 1 second.
click the share content, and instead of screen, don't share the screen. Go to the application, and from there you select the PPT.
Okay, so I'm looking for. There is a more options. Yes. Murthy, I don't see an exclusive app option, but what I see is more options. Yeah, okay. And then it says copy meeting link, audio connection. Share content, okay. Yeah, on the top I'm seeing this. Okay. 1 second. 1 second. Other applications, huh? Okay. It says other applications. No, Baba, it's not coming. I am using Chrome. Okay, so I continue with the screen option. Would it be that some of you have your speaker on and hence the echo is coming? Is that a possibility? No. Are muted. Okay, okay. All right. So, but now it is unresponsive. So shall I just log off and log in? Yeah. All right.
Dear participants, kindly bear with this small technical glitch. Dr. Tiju Thomas will be logging in soon. Thank you.
Are you able to hear me now?
Yes, Tiju.
Is there echo now? Is there an echo now? Now it's fine, no? I see.
Yes,
Got it. So I think I'll continue now. Yes. Okay, perfect. Screen? Are you all able to see the screen?
Yes, Tiju. Yes, Tiju.
Wonderful. All right. Okay, so so I wanted to explain the luminescence mechanism, and what I wanted to point out is you could actually think about a bunch of atoms sitting together where the central atom has line spectra, much like the hydrogen atom itself, let us say. But it is bonded in such a manner such that it easily gets excited when it absorbs a photon, and then it relaxes, comes back, and in the process you have an emitted photon. So this emitted photon would be the light that falls on your eye. So lattices typically are what I call as structurally rigid. So the lattices are chosen to be structurally rigid, and there is a reason behind it. We won't go into the details there, but you will find that such lattices find applications in a wide range of technology, including defense technology. So here is an example of all the applications of materials that are typically nitride based and which have very robust lattices. So you will find that from the world of radar to the world of missiles to the world of communication, and not only in lighting, you will find applications for these kind of materials. So we in our group do make these materials. So for instance, this is a schematic of a reactor that was built, and this reactor currently has a throughput of roughly 100%, close to like 99.5% or so. And that means the yield is very high. And this was the first such reactor to give a yield of almost 100% for this material. And not only that, it actually emits very well. So let me just take one of these and show it to you. So this was duly excited, of course. And so it was duly excited. And when it was duly excited, you get the 620 nanometer very sharp peak. And the 620 nanometer very sharp peak basically means it is red. Now, the good news is for the blue LEDs that are coming in the market, you could put this on top of that. So you would be able to excite this material using blue. You would be getting blue plus red. And if you invented a material for green, then you would get red, blue, and green. And then you would be making white LEDs here in India by using our own native technology. And that would be a very nice thing. And as I said, there is a lot of prospect for this. So we made something of a very simple device in our lab. This is built by using what is called as, this is a simple electrophoretic tool. And this simple electrophoretic tool was made by using very simple colloidal science. So instead of thin film technology that depends on vacuum, I wanted to make it very low cost, very scalable, in principle, something that can give rise to an industry. And here we developed this. It's called an electrophoretic thin film deposition process, wherein you can have an electrode, you can have a working electrode, and in between you have a dispersion. So this line that you're seeing here, that line basically marks the dispersion. So this entire jig here is sitting inside a colloidal dispersion, which has nanoparticles, and the nanoparticles get deposited to the surface of the working electrode. And this is how we were able to get very thin films. This was sort of exciting because now you could then dab electrodes on top of it and make something like a red light emitting device. And some of you who are from the sciences, you like to see not just results like this, but you would like to also understand what is happening. So we did some high pressure measurements and high temperature measurements, low temperature measurements, in order to understand the mechanism of luminescence in this material. We have been over the years also inventing other materials that have prospects for use in light emission applications, such as this. You can see it is a very complex composition, complex looking composition, but it does very well. It can be excited by using blue. You can see this in the slide below, in the picture below, and you get red. So we have been combinatorially also designing materials that can be useful for LEDs, and we have been exploring the full rainbow. So we have been publishing in this space for a while now, and we are increasingly also trying to generate patents so that this gap that I told you about, that is present in India, which is this huge gap. It's not just India. You can see most of the world has that gap. And the reason is because I believe they don't take into account scalability and greenness indices when they come up with device technologies. So if you are an engineer or a scientist in this generation, you should start from there. Start from the question of scalability and greenness, and then say, how do I invent so that industry comes up? So that is sort of how I would say you have to go about innovating. So that has been our model for innovation. And after the innovation, there is, of course, possibility of science. So there is possibility of publications and so on. So you can do all of that you're doing right now. But basically, at some point, put on the thinking hat. Say, will my technology be useful 10, 15 years from today? If it is not going to be useful at that point, then maybe you should be more visionary in your approach. So this is a paper that came off that kind of an approach, and it has been one of the editors' pick for one of the years. So moving forward, there are device fabrication approaches also that is going on here in IIT Madras. And we have been growing solutions and growing nanostructures using very low temperature approaches. This is a nano jungle for all practical purposes, all of which are vertically aligned, zinc oxide nanorods, and they were used as current collectors in a solar cell. I didn't have the time to get into the details, which is why I put this as a collage. And the good news for you is that wherever you have charge collection application, you can grow by using chemical bath deposition processes by averting the need for vacuum, which is usually the challenge associated with scalability in many, many countries. So this is a paper that shows that. Now, what are the other areas of research that are going on here? Well, this is a snapshot of areas from the bio end of things. The previous talk was bio oriented, to the highly applied petrochemical or water oriented things, to thermochemical, thermoelectric kind of work, to batteries. These are all the kind of work that is going on in this campus, solar cells and so on and so on. And I must say it is not true just for this campus. This is a very good academic corridor. So Chennai has a large number of universities that are not too far from one another. I believe that is in some sense true for Coimbatore also, because you have SREC, PSG, etc. So if you come together, you can do amazing things. And that is really what I'm realizing when I'm working here in Chennai also. There is something may not be here, but it might be there. Some expertise may not be here, but it may be there. So I think the PhD program today, more than ever before in India, should sort of allow for this kind of freedom. And I think it would benefit students and faculty, and most importantly, knowledge creation that is relevant to the society if we did so. So in and through these conversations, we also realize that the kind of approach, the engineering approach we take, the green technology approach we take is very useful for solving some of the water problems in India. So I wrote down a perspective article that focused on, I'm sorry, I'm having to do this time and time again. And that is because, as I said, when I'm putting it on the full screen mode, it is not functioning. So there is some technical glitch, but I'm trying to make do. I hope you accommodate me. So this is sort of how usually a water treatment plant looks like. So I visited a few water treatment plants, and I basically identified a place where you could put something called a photocatalytic reactor. And I'm aware that in SREC there is some activity to this extent that is present, but I do not know if you have thought of it in the practical sense, that is making sure that the PCR is actually placed in an appropriate place in a larger comprehensive water treatment plant. And this is a project that is going on, and the United Nations, for instance, is also now pushing for something of this sort by through their policy documents that they're issuing to the environmental protection agencies and so on, because the conventional water treatment processes have their own strengths, but they also have their own severe weaknesses. For example, the ROUV component can actually be a very significant environmental threat, but it is very rarely studied or even expressed. But if you actually had a way to carbonize and mineralize content here by using PCR, you would be reducing the load on ROUV system here, and that would make it much more sustainable. So one of the papers I wrote was more on the policy side, on how technology should be developed in this end. And as I said, it has sort of picked up some traction over the last few years. Now, coming back to the sciences, you will find that zinc oxide, for instance, which is a little bit like TiO2 that we had discussed earlier, very, very easy to make. But the problem is it doesn't absorb much of sunlight if you wanted to use it as a photocatalyst in, let us say, the kind of reactor that I showed you here. I showed you some kind of a reactor here. And the question is, how do you use a material that is dirt cheap, easy to manufacture, etc.? Zinc oxide would be one option, but the problem is it doesn't absorb sunlight at all. And here we were looking at one way to engineer the absorption spectrum of zinc oxide by using copper, not just as a dopant, but also as some kind of a semi-coat. That means you actually have a heterojunction. So for lack of much time, I would just say that we not only have copper inside of ZNO, we also have copper that is somewhat dabbed on top of ZNO, and that gives rise to very, very good absorption. And not only that, it enhances the photocatalytic performance by a factor of about 3 or so. So it makes it a much more efficient process. Plus, this process was carried out at room temperature. So the usual challenges associated with high temperature and sustainability, industrial production, scalability, etc., gets bypassed. So that is the advantage of having this as an approach. Now, before I go further, I wanted to show you another example wherein this approach has been used. Now, this is a reactor, this is a schematic of a reactor, and many of you, I believe, are from the nanotech space. So you would, I think, understand at least chemical formulae. So these are a set of compounds that are actually placed in a strip-like fashion beneath the beaker, And it turns out that when placed in a stripe-like fashion and when jigged in a particular manner, it tends to become a very, very good adsorbent. Now, this was an interesting result, and we rationalized it by using both transport phenomena kind of arguments as well as thermodynamic arguments. And in all of these cases, the material that was used was very cheap. So you can see zinc oxide was used, this was used. All of them are earth abundant. So we deliberately stayed away from materials that are costly or not earth abundant. So another class of problems that we look at here in my group involves ultra small materials and their instabilities. So for instance, you might have a situation wherein you have a very large collection of particles, let us say quantum dots, and they follow a very broad particle size distribution. And the question you can ask is post facto. That means after you synthesize these particles, is it possible for you to make it into a near delta function? That means, can you make the histograms such that all of them are the same size? Why would this be important? Because in the quantum mechanical regime, it turns out that size matters. If the size is exactly the same, all of them would have exactly the same electronic structure. So size matters, and this has been an activity that has been going on for a while in the group. And we have now come to develop a few stories, not just with zinc oxide, but with other oxides as well. Potentially, it can be extended to other materials as well by using hard acid-base interaction approach to choosing surfactants that allow for particle sizes to go from what looks like this to what looks like this. And as a consequence, ensuring that the particle size distribution goes to near zero. As engineers, we also like to model this. So we wrote out equations and did self-consistent field calculations. Believe it or not, this was done by using a free software, and I used what's called as an agent-based software. It's very, easy to learn language. And once you learn it, you can actually play with these equations. Now, these equations are colloidal chemical equations. The first part, if you have taken a course on colloidal chemistry, you might recall it is called the Gibbs-Thompson's part. The second one is to do with mixing entropy. This part was added in by hand because these particles have electrostatic interactions. And then with the set of these four equations, we started seeing mu versus radius starts showing some kind of a minima. And that is the reason for this collapse in particle sizes from what would otherwise be a jungle of particle sizes to a single particle size. So this is very exciting because there is nothing in this equation that requires you to believe that it should work only for oxides. It could work for nitrides, sulfides, oxysulfides, etc. So people could just explore by using a combination of what we have reported here plus the hard soft acid base principle that I said, which I must also cite Professor BLV Prasad, who is in NCL Pune, his work on. He worked primarily on metals, but he did not do the modeling, by the way. But then we used that model in order to see whether it works for oxides, and then we modeled it. So now with this model in place, we have the ability to design experiments, and that makes it rather interesting. For the more chemistry-oriented people out there, this gives you an opportunity to play with surfactants so that you go from polydispersed particle sizes to monodispersed particle sizes. We also derived a law where the particle size is written as a function of the logarithm of the solubility product of the particle in the solvent and the critical concentration beyond which saturation occurs. So this law came out of those equations and the model that came thereof. So we have a nice formula now. So let us say that you generate 3 or 4 data points and you find A, B, C for your own system. Then you can say, okay, this is how I should play so that I have a convergent particle radius of dash and whatever that dash may be. So you could do this for sulfides, oxides, oxynitrides, chalcogenides, whatever you can think about. Because as I said, these equations are agnostic to that. So this is the particle size flux. So when you believe that these equations are operational, that is equivalent to saying that particles, the larger ones dissolve away into smaller ones, the smaller away ones dissolve into larger ones, which is the opposite of what you have studied in Oswald ripening in some of your courses. In some of your courses, you will find you have studied Oswald ripening, where the small particles get subsumed into large particles. But in the colloidal regime, there exists a regime wherein the small particles can draw atoms from the large particles, just as the larger ones draw from the small particles, and eventually they all happily converge to a single size. Now, at these size regimes, what happens at the junctions of these particles? So we have been looking at that or problem also, and looking at it as a heat treatment problem. And there is much to talk about, but at this point I will stop because I think I've already taken up my time. So we work on a wide range of material problems involving energy and environment. So water research is one such area, and also at the interface of water research and solar research is another area. We are running into some very exciting possibilities there, and we hope to set up a company there, for instance. So the PhD students who made those inventions and discoveries are interested in taking it forward towards the establishment of company. And I hope this also gets PhD students and MSc students there excited in SREC and other places, wherein you see prospects and you think prospects. And if you solve a major problem, maybe there is a market out there that you can actually cater to, and a social problem out there that you can solve by using the science you have learned. Then we have been looking at quantum nanostructures, both for device as well as for modeling purposes. We enjoy the way they behave and how their properties evolve as you go down in size. And in particular, we have been looking at ultra small particles, and we have been using them for a wide range of properties. In recent times, we explored the possibility of using them not just for lighting, but for charge storage. Now think about it. That would be a very exciting thing, isn't it? If you could charge store, you could charge store in a switchable manner and then get light. That would be very exciting. So we are doing things of that sort. And then there's bond valence based approach that is going on. So many thanks to the very many young researchers on board who burn midnight oil and make all of this possible. I must say I'm like a very free spirited guy. So I just ask people to think and dream, and sometimes those dreams come true, and that's a wonderful thing. And in the past, there are people who have graduated from the group who have gone on to various R&D centers and so on in various parts of the globe, but who continue to be in touch. So I'm very grateful for having good people on board. And let me stop with this. So this is a little bit about my department and all the things that goes on. It is a very limited slide in the sense that it doesn't capture everything that is going on, but there is some bio dental work, there is some bulk processing, nano processing, metallurgical work, welding, and then a lot of computational materials engineering. It's one of the strongest in that area. And then metal forming, mechanical behavior, iron and steel. I think country's only iron and steel center is here right now. So the Tatas actually have a strong hold on that. But these will all function by and large as a hub and spokes model. So if there are colleges out there that would like to actually strengthen in any of these areas, and they would like to use the strengths that are present here, we can learn from one another, build bridges, for instance. And the active, I made a slide basically to help you know what are the things that are going on, who are the people, what are the names. So my colleagues, I put their names also here. I must also here tell that with SREC, I have very close ties. This is just the IIT Madras slide. I have another slide which I couldn't put together because of a hurry. But with SREC, we have very strong ties. Leggins, who is one of your alums, played a very crucial role in building bridge between Professor Murthy and myself. Professor Murthy, who is one of the organizers of this webinar, and he and me go a long way back. So for all practical purposes, I've known him for 1/3 of my life. I'm very grateful to him. And if there are more possibilities of interface with SREC, I would only be delighted. And there are all these prospects that have been opened up. One more thing that is prospect oriented. So over the last 4 years or so, we have tried to set up a national center here focusing on solar energy harvesting. And I'm one of the coordinators for this. So not that it means much, but it actually at least means that I know whom to contact for what if you have a particular need or some such. So I'll be happy to help in that sense. And the 4 verticals that operate in the center right now are photovoltaics, which primarily, I must say right now, because it is so industry driven, It is only silicon photovoltaic, so there is a limitation there. But you could get creative in SREC, for instance, if you have a solar simulator there, but use the expertise that is available here for defining problems or so. Solar fuels, I'm quite embedded in that area of research, and there is some information that the government of India will push for that in future. This was certainly this is pre-COVID data that I'm telling you. I hope that continues to be the same after COVID lockdowns, etc., get lifted, and I hope government remembers its policy, its own policy documents. Energy storage, very important. With or without COVID, that will be very important. It is becoming very, very clear. Solar thermal also, same is the story. With or without COVID, that will remain an important area of focus for the government. So those of you who are planning to start companies, etc., based off your lab, you can keep these things in mind. And if you want to know a little bit more about the government thinking side of it, I would be happy to share whatever I know. I am not the government, but I have to, unfortunately, interface with funders and so on. And in the process, you get to know a little bit about the mood of the government, which in some sense gives you an idea, especially as PhD students, where prospects might lie 3 years down the road. And that has been my strategy for the PhD students and postdocs who work with me. So thank you very much for the attention. I apologize for all the technical glitches and for all the hassles you have had to deal with as a consequence. But at this point, I'm happy to take questions.
Dear Tiju, thank you very much for your nice and wonderful presentation. I request the participants to unmute yourself, and if you have any specific questions, kindly share the questions, please.
So how do I see the participants? Because it would be nice to know that they are not robots, you know. So
I think few participants they had not shown the video, but
I see.
few of
That's
them
okay.
they have any
No,
questions.
I was just joking. I was just joking. Yeah, yeah.
They will unmute and they will ask the questions.
Yeah, sure. Yeah. So any one of you, by the way, no question is silly. Answers can be very silly. So you can anticipate me to be silly in responding to you, but your questions will never be silly. Yeah. So feel free to ask.
Good afternoon, sir. I am Dr. Nanomaterials.
I'm not able to hear you, but you can talk. Maybe somebody is hearing you and they can help me understand you. Who is this?
I am Dr. Nanomaterials.
Okay, Dr. Nanomaterials. Good afternoon.
Yeah, good afternoon, sir. So, how you are using these same things in the thermal barrier coating is possible in the nanostructure in the below?
No, I did not show anything on thermal barrier coating, sir.
Okay, sir.
I didn't show anything, but I can tell you because I teach this stuff. If you want to, I mean, there are design principles for thermal barrier coatings. So it depends upon what you want to aim for. Like, is this part of your research, Dr. Nanomaterials?
It is a part of my research only, sir.
Okay, so see, there are two things that you can think about when you're thinking about thermal transport across two materials. What happens is, let us say I have a material A sitting on top of material B. Then for good thermal transport to happen between A and B, you need two things. One is, let us to begin with, assume that A and B are crystalline, in which case both A and B should ideally have similar lattice constants and crystal structure, and importantly, also similar what are called as phonon density states. So this is something that can in principle be predicted. All right. So what I find people doing in literature is they try all sorts of things and then it's all hand wavy arguments. I think a much cleverer way is possible if you actually consider this as the design criteria. And then you might be able to identify the materials heterostructures that will work for you, Dr. Nanomaterials. So
thank you, sir.
To help you, I could be, I mean, for instance, see, just yesterday, somebody from Intel actually reached out to me or something along these lines only. So you can, and I was basically telling them the same. But the devil is in the details, as they always say, you know. So the formalism for this needs to be laid down, and we need to actually build a platform for that. So that is what I was trying to discuss with Intel group yesterday. I don't know what will come out of it, but there is definitely a lot of interest, not just for thermal barrier coatings, but also for all applications wherein heat exchange across junctions are involved. And for building a nice platform which captures the interfacial heat transfer resistance is important. It's also called the Kapitsa resistance. But sir, in today's
Yes.
presentation, I didn't talk about any of those things because I wanted to keep it purely energy environment engineering, the big problems in India and how some of the research we do might be helpful for that and so on.
Okay. Thank you, sir. Thank you a lot.
You're very welcome, sir. And as I said, I'm a good friend of Dr. Murthy's, and you can take a number from him. I also know Dr. Daniel Tangaraj very well. I've come
Oh,
here for his students' PhD defense and so on. So you can
oh.
take my number from either of them, and I'm happy to be in touch with you.
Okay, sir. I will touch with me.
Yeah,
Later.
sure.
Thank you. Thank you a lot.
You're very welcome, sir. May I know where you work?
I am working at Anna University, Viluppuram campus.
Oh, I see. Very nice. All right.
Okay.
Good.
Thank you. Thank you.
Wonderful.
Thank you very much.
Dear
Any other
participants,
questions?
if you have any other questions, kindly unmute yourself and you can ask your questions, please.
So I would like to have some questions from PhD students and MSc students also. So if not, I will request both Professor Murthy and Professor Daniel Tangaraj to conduct very, very hard exams for you. So you have two choices. One is ask questions now or be prepared for very hard questions from Professor Daniel and Professor Murthy.
Dr. Tiju, there is a question in the chat box.
I see. Okay. Let
Sir,
me
in
open
terms of
that.
barrier properties for packaging application, which polymer is technically gives better properties, amorphous or crystalline or semi-crystalline?
Yeah. So you are asking questions that have nothing to do with my presentation. Does that mean that my presentation was not interesting to you? Who is this? Sundar N. Sundar, you can talk. Are you there, Sundar?
Hello, sir. Good
Hi,
afternoon.
Sundar. Yes. So what are
So,
you, Sundar? What's your background?
so I'm a MSc chemistry student.
MSc from which background?
Chemistry.
Okay.
I'm just doing the PhD also part time.
So you are now, you have an MSc in chemistry and a BSc in chemistry, is it?
Yes.
Okay.
My
All right.
question
You're
is
doing a part-time PhD.
Yes.
Okay.
So
Very good.
my question is there in terms of I asked two questions. One is in terms of polymer that's not covered in your presentation. That is understandable. And in terms of fillers, nano fillers, what is the crystallinity plays a major role?
Yeah.
That's my
Here,
question.
I mean, though not covered in this, I teach things of this sort, so I can answer this question. Okay.
Yeah, sure,
So
sir.
here is my response to your question. So polymers typically, no matter what your cooling rates are, tend to be at best semi-crystalline with a crystallinity of not more than 30%. If you have a
Okay.
crystallinity that exceeds 35%, it's considered a highly crystalline polymer. So that is in the world of polymers. All right. Now,
Yes.
typically, the higher the crystallinity, the larger will be the thermal conductivity. So,
Okay.
what kind of barrier are you talking about? Are you talking about thermal barrier or barrier to viruses given the corona situation? What barrier are you talking about?
A barrier to the moisture, air, particularly gases.
Yes. So typically, so one thing is for sure. I mean, again, there is no general rule here. On an or as a thumb rule, typically as the material becomes more and more amorphous, there is a possibility, especially if the species that is diffusing in through the amorphous material is not strongly interacting with the coordination the environment that is available in the amorphous material, then the diffusion coefficients tend to be very high. On the other hand, if you have the species which interacts very strongly with the functional groups that are present in the polymer, let us say, then you might end up having a situation wherein having more amorphous nature would mean higher barrier. So you have to be, as a consequence, very careful. See, this takes me to literature where there was a lot of debate on
Okay.
diffusion coefficients of high entropy alloys, for instance. So for a long time, people said, you know what, HEAs will have very low diffusion coefficients because they are so disordered. It turns out that it is only on a case-by-case basis. It has
Okay.
to do with how the given species interacts with the coordination that is available in the lattice or in the medium that it is going through.
Okay, sir.
So it is not, so you will have to then say, okay, if it is moisture, then do I have groups in the polymer that will interact strongly with water molecule? Okay,
Okay.
if it interacts strongly with water molecule, then the answer would be very different from if you say it doesn't interact very strongly with water molecule.
Okay.
Okay, and you could also think about graded polymers, which you know is available in literature, wherein you could actually grade it in such a manner that there is a gradient of functional groups that allows water to seep in through the material. That could be a very clever thing to do, and if you can show it, it might be a very nice invention.
Sure, sir. Thank you.
Yeah.
Sir, one more question that I used to
Who is
read.
this? This is again Mr. Naveen, is it?
Sundar.
This is Mr. Sundar. Okay, okay, okay.
Sir, one more. I used to read most of the articles, but most of the inorganic nanomaterials, even
Yeah.
they are concluding in most of the articles saying that through FTIR, they are saying that only physical or there is no much interactions. I can come across most of the articles. There is no new bond is formed or
Between the
only.
polymer and the inorganic
Yes,
materials.
yes, yes. So what is the
Yeah.
main reason, sir?
See, you will have to think of it thermodynamically. So you remember, I don't, in your thermodynamics course, in your MSc or BSc, you must have studied about phase segregation.
Yes.
And under what condition does phase segregation happen? Well, phase segregation happens based on something called regular solution interaction parameter. So you
Okay.
will have to actually evaluate the enthalpy of interaction between the various competing bonds, and based on that, argue for why bonds exist where they do and why bonds don't exist where they don't. But it has to come ultimately down to the enthalpies of the various bonds that are in competition with one another when you're
Okay.
making these composites.
Okay.
Yeah. Any other questions?
Yes, thank you, sir. Very nice. I
You're
now I
very
am clear.
welcome. And as I said, I'm happy to be available for just brainstorming or discussion. I'm good friends with Professor Daniel, Professor Murthy. So you're most welcome to reach out to me through them. You can just take my number from them, and I am somewhat available on WhatsApp. I'm quite available actually. So for short questions like this, maybe it'll help you save some time for your PhD, and that would be a good thing. Yeah. So yes, any other questions? I'm just going through the chat box. There are some people asking about internships. Now you see, given the situation, we have my own students are not on campus, so all the projects that are going on are computational. So if you're interested in computational programs, some interest in programming, etc., then you can reach out and maybe I can give you a problem or two. And yeah, so things of that sort. Because see, I don't know if you know the stance of the institute. The right now, what we have realized is is happening across the world. We don't know when we will come back on campus because the situation is very, very, very bad in Chennai. So that is the situation. So what we can do is, if you are interested in computation in particular, and I'm increasingly interested in computation, I must say. So I mean, I think there would be possibilities that opens up. Otherwise, I'm very interested in experimental design. And if you have facilities A, B, C in your campus, and what you need is a brainstorming space to identify how to make best use of it, you can use me. And that way you can be where you are and while still doing internship with whomever is there and me, and that would be a perfect thing to take forward. Yeah. Yes. So many of you are very kind. You have said that this presentation was helpful and informative. Thank you so much. Thank you so much, all of you. Then there is a professor of statistics here who I believe he wanted to ask a question, but I didn't get his question. Dr. Joshua Joseph. So,
if
Dr. Joshua, you wanted to ask some questions? Or maybe I'm running out of time. Murthy, do you want to cut me off?
Yeah,
So,
this is Daniel. If you
yeah.
answer all the questions, whatever you have seen in the chat box, I think you are done. Thank you very much for your
Thank you.
presentation and accepted
Yeah.
our invitation.
Yeah.
Stay safe at Chennai.
Yeah. Daniel, just one quick thing.
Yeah, please.
Some people were asking about the job prospects, and maybe you can advise them on the same. But most of the manufacturing sectors would definitely take MSc material science students. Okay. So think about some kind of industry engagement during your MSc PhD itself, and maybe that will enhance your industry orientation and make you more viable as and when you apply. So that would be my 2 cents worth for Naveen and others who asked job related questions. Yeah, I am done otherwise.
Yeah, thank you, Tiju.
Thank you, Daniel. Thank you, Murthy. Take care. Yeah,
Yeah,
bye-bye.
thank you. Now I request the convener, Dr. Murthy, to deliver a word of thanks.
Dear participants, thank you very much for joining this one-day webinar on diverse application of nanomaterials. On behalf of SNS and Charitable Trust and on behalf of our institution, Sri Ramakrishna Engineering College, and on behalf of our Department of Nanoscience and Technology, we extremely thank all the speakers, Professor Dr. B.S. Murthy, Professor Dr. Balakumar, and Professor Dr. Tiju Thomas, and all the participants who have joined this one-day webinar. I just give the email ID in the chat box. If you have any feedback or suggestions or comments for improvement, you can write to us. Kindly follow the instructions laid by the Government of India, Government of Tamil Nadu, and local ministries, and follow the health instructions. Please stay safe. Thank you very much.
All right. Take care. Bye-bye.
Thank you, Tiju. Take care. Bye-bye.
Thank you. Bye-bye. Yeah, bye all of you. Thank you for joining.
Bye-bye.
Bye.